our past, present and future. Because in the end, we are all nothing but atoms.
Which is Raman spectroscopy received a was one of the 1905, but it found little acceptance for nearly 2 decades. And the Raman effect was one of the discoveries which made it very electronics, you name it.
When Raman was appointed to the Palit chair, the impression began to be created. People indeed.
He was an extravagant.
That Raman faced in his
all this money for buying equipment.
and understood.
Pay attention to that, and yet in his book he pays no attention to that. He talks all the time of what happens in the light, in the way light acts on the retina, but he pays no attention, and by then. I don't think Raman really discovered anything or added anything to our understanding of vision. There are 3 major tenets of the theory of vision or modern theory of vision, with each one of which Raman seemed to have taken issue and disagreed. He totally ignores what the contemporary knowledge of physiology of vision was. It's what goes on in brain which constitutes perception, and you have to pay attention to that. And yet in his book he pays no attention to that. He talks all the time of what happens in the light, in the way light acts on the retina, but he pays no attention, and by then actually a fair amount had begun to be known about how information reaching the eye is analyzed by the brain. And really key to understanding the perception of color is in understanding that, and how brain analyzes the signals which go from the eye. So that sort of is, one has, it only can evoke in one sense a feeling of sadness that a mind like that essentially had decided to cut himself off from what the science was.
When he made his discovery, he was already 40 years old, and thereafter he was not able to hold his own and keep pace with the new trends, new fashion, and new style. And this shows up clearly in the controversy that he had going with Max Born for many years on a rather technical point concerning the subject of lattice dynamics. It was clear that Raman was partly right, and he was not totally wrong, but yet the way he made his arguments, people dismissed him, and he was forced to obscurity thereafter. Many people in his generation, of course, suffered an eclipse, but they did not suffer controversy, so one doesn't notice their eclipse. In the case of Raman, unfortunately, the eclipse is very prominent because of the controversy.
Although certain aspects of Raman's personality and work have been criticized, there is no doubt that he was instrumental in laying the foundations of the entire edifice of Indian science. Apart from physics, he was equally interested in the growth of the other fields. These fields were not to be developed in isolation, but in relation to each other. Science was a living, dynamic whole, and ideas needed to be exchanged. So he created a national forum, the Indian Academy of Sciences. He also wanted science to reach the masses. His popular lectures were always comprehensible and tinged with humor. Children were the future of the nation. To them he wanted to gift the joy of discovery. This, then, is the legacy of a man who believed in the potential of the Indian mind.
What we lack is perhaps courage, driving force. We need a spirit of victory, a spirit which will recognize that we, as inheritors of a proud civilization, are entitled to a rightful place on this planet. If that indomitable spirit were to arise, nothing can hold us from achieving our rightful destiny.
Raman died on November the 21st, 1970, here in Bangalore. He was 82. His death marked the passing of an era in Indian science. A unique memorial marks the spot of his cremation. It is, as he himself would have wished it, this solitary tree.
Unraveling the mysterious universe and understanding its structure has been an insatiable curiosity of mankind. India has a long history of astronomical scientists. Aryabhatta, who interpreted that the Earth rotates about its axis, Brahmagupta, who gave the formula for cyclic quadrilateral, used often in astronomy, and Bhaskara, who determined the parallax in longitude. In the recent times, Subramanian Chandrasekhar, Jayant Narlikar and Meghnad Saha are among a few Indian astrophysicists who took the world by surprise with their cosmic discoveries. Holding the proud legacy, our scientists are an integral part of the world's biggest mega science projects. Mega science projects often involve cross-border cooperation between teams of competent researchers. While the scientific goals of these projects are significant, their worldly benefits are equally important. By collaborating, participating and delivering components for these giant projects, India places itself as a major player in fundamental science globally. In addition, these projects have the potential to create new avenues for science-industry collaborations and to popularize science in the country. Taking the same theory of gravitational waves forward, Indian scientists are designing an advanced gravitational wave observatory. This project is a collaborative project between a consortium of Indian research institutions and the LIGO laboratory in the USA, along with its international partners Australia, Germany and the UK. LIGO India bring forth a real possibility for Indian scientists to step forward into the frontier of an emergent area of high visibility to probe the universe.
The site selection was a mammoth effort. It took 5 years. So from 2011 end, we have been looking at sites. We followed about 40 site leads all over India. The main challenge was we needed stable ground in terms of low seismic noise. So you have to go to places which are known to be stable and the low seismic risk zones. Secondly, we also needed to be away from people, and that's a challenge because we also need people to run such a big facility. So we had to balance between finding a place which was reasonably big so that people would love to work there, but remote enough that there are no disturbances. We can't have roads within 10 kilometers of the site.
The fact that this location is in India, is its biggest plus point because it's far away from all other detectors. The US detectors are almost on the other side of the earth. So this is almost the biggest baseline that we can get for a network of detectors.
What really excited all of us was the fact that this experiment essentially included technologies of various types.
With zeal, determination and immense opportunities opening for astrophysics both in national and global front, it won't be long when our scientists will dominate the world arena with their hypotheses and discoveries, devising their technological know-how to make our country proud. The various technology transfers in India, driven by innovations from our scientists, also open gates to welcome large foreign investments and large investment flow into the country. With the recent breakthroughs in the astronomical world, India, with its exemplary technical capability, not only takes a leading role in executing large-scale projects, but also goes several notches up globally in terms of research and discoveries. mysterious universe and understanding its structure has been an insatiable curiosity of mankind. India has a long history of astronomical scientists. Aryabhatta, who interpreted that the Earth in Lothian of the world's biggest physicists. Brahmagupta, who gave the formula for cyclic quadrilateral, used often in astronomy.
The contribution of women in the fields of science is perhaps one of the less explored subjects globally, and even to this day there are fewer women pursuing scientific fields or STEM than men globally. For women in India, the challenges of pursuing the myriad fields of science during the British Raj and the years leading to India's independence on August 15, 1947 was difficult to say the least, as there were only limited opportunities. Higher educational institutions started by the British were limited when compared to India's population and geographical spread, and most of them were for men. The situation was even more complicated for women due to traditional circumstances in India of not encouraging education of the girl child, let alone giving them opportunities to pursue scientific fields. But for many women in India, these historic conditions, though difficult, were not insurmountable. As we celebrate 75 years of India's independence, we also celebrate the lives and contribution of women who cracked the glass ceiling and pursued science in the 19th and the 20th century in India. They were pioneers who fought against discrimination as well as societal and cultural barriers of keeping women out of educational institutions. So in this two-part series of Science for a Self-Reliant India, we first explore the lives and contribution of some remarkable women, like Kadambini Ganguly, the first qualified doctor of India who studied medicine in Calcutta Medical College, E.K. Janaki Ammal, botanist and cytologist, Annamani, who excelled in the field of meteorology and physics, and Dr. Ashima Chatterjee, who excelled in organic chemistry and phytomedicine.
Women like Kamla Bhagwat at that time, who later on became Kamla Sohani, who did her pre-doctoral work here and then went to the UK with a scholarship where she did some very important work on cancer. Kamal Randive, Kamla Sohani, these are the early women scientists that I can think of. Then came Professor Janaki Ammal, who was the first woman to get a PhD in a US university. Then there is Professor Ashima Chatterjee, who got first woman to get a PhD in chemistry in India.
This and much more in our show, Science for a Self-Reliant India, only on India Science. As we celebrate Azadi Ka Amrit Mahotsav, which commemorates 75 years of progressive India and the glorious history of its people, culture and achievements, it is only befitting that we remember the important role of Indian women scientists in the 19th and 20th century, whose contribution to the field of science and education is now part of our country's rich legacy. In this series for Science for a Self-Reliant India, we pay special homage to these determined and brave women who fought against gender discrimination in education. They were ahead of their times, and while we can only bring to you the lives of only a few luminaries in these episodes, they represent all the women scientists who have enriched our country's educational ecosystem by bringing in gender parity and contributing to the fields of science on an international scale. So let's begin our episode by taking a close look at Kadambini Ganguly, the first qualified woman doctor in India. Madras Medical College was the first institution that allowed and admitted women students for the first time in India in 1875. This was an era when only one institution in the United States, the Women's Medical College of Pennsylvania, established in 1850, was open for women who wished to pursue medicine, while there were none in Europe. After Madras Medical College, The Calcutta Medical College, then known as Bengal Medical College, started admitting women in 1884, while Grant Medical College in Mumbai followed suit in 1887. But in the initial years, no Indian woman was able to qualify for admission in the medical colleges until Kadambini Ganguly, a graduate with a degree in arts, was finally admitted to Calcutta Medical College to pursue medicine in 1884. Kadambini Ganguly was born on 18th July 1861 as Kadambini Basu in Bhagalpur, Bihar, and was raised in Changi, Barisal, now in Bangladesh. She completed her formal education from Banga Mahila Vidyalaya, later merged with Bethune School. She became the first candidate from the Bethune School to appear for the University of Calcutta entrance exam and created history by becoming the first woman to pass the test in 1878. Kadambini was also one of the first two female graduates, along with Chandramukhi Basu, in the entire British Raj. After her graduation, when Kadambini decided to pursue medicine, she found that no medical college in Calcutta was admitting women students. But due to her persistent efforts and those of Dwarkanath Ganguly, a teacher and husband of Kadambini Ganguly, she was finally given a chance to appear for the entrance exams. And having qualified, she became the first lady to be admitted to Calcutta Medical College. She completed her education in 1886, even with hindrances and challenges that came in her way, as the authorities were not in favor of admitting female candidates.
Before 1947, if I have to talk of women in science, I have to begin by talking about women in education. Women who learned, first, because women until 1880 or so, they were not even learning to read and write. And therefore, the early women achievers, or scientists as I can call them, are actually medical doctors. And most of them were taught at home very often by family members, fathers, brothers, husbands. And about them I can talk about, Anandibai Joshi, Kadambini Ganguly, who were the first women doctors to get training as doctors. And I think one thing I would like to mention here, which is very nice, is that this is about the same time when in the rest of the world also women started becoming doctors and surgeons. So India was kind of in step with them. Then, of course, there were these women like Mary Lucosa, who was the first woman surgeon, who had a lot of support from Travancore king to go and study in the UK. And she was taught by some of the women who were first surgeons in the UK. So this is just to tell you that we were at the same time. So the first women who had something to do with science in India were actually medical doctors.
1886 was also a remarkable year for women's education in India, when two women qualified to become doctors in Western medicine. Kadambini Ganguly was of course one of them. Along with her, Anandi Gopal Joshi, who studied at Women's Medical College of Pennsylvania in the United States, also qualified as a doctor in 1886. But due to her ill health, she could not practice medicine and died in 1887. Thus, Anandi Gopal Joshi is considered the first Indian woman to be qualified as a doctor, and Kadambini Ganguly is considered the first Indian woman to practice her profession as a doctor. A few years later, Dr. Kadambini decided to pursue higher education in England and went on to complete 3 diplomas, namely Licentiate of College of Physicians, Edinburgh, Licentiate of the College of Surgeons, Glasgow, and Licentiate of the Faculty of Physicians and Surgeons in Dublin. Dr. Kadambini Ganguly also specialized in pediatrics and gynecology. Dr. Ganguly was also associated with the freedom struggle and several social movements of India. She was also a part of the first ever female delegation to attend the Indian National Congress in 1899 and was selected to vote in its 5th session. Dr. Kadambini Ganguly openly spoke against Calcutta Medical College's practice of not admitting female candidates at the medical conference of 1915. It was a provoking lecture that led the university authorities to amend their policies and open their doors to all female students. Dr. Kadambini passed away on 3rd October 1923.
Madras Medical College was the first to open its doors for women, and later came the Calcutta Medical College and so on. So at that point, I think 1885, because women's health was very important, and as the colonial rulers themselves needed medical facilities, a fund was set up, Dufferton Fund, to enable women doctors to come into India and also to train Indian women into medicine. And that is the one, that is why, at that point, Anandibai was able to go to US. And there was only one institution in US offering medical education to women. And in Europe, none. But in India, the medical colleges of Madras and Calcutta did open their doors to women. And at that point, I think education for women, though not prevalent, but began to be available. And if you look at one of the oldest colleges, the Bethune College in Kolkata, and the alumni that it produced at that point and the role that they played in politics, in social activism, it is immense. So Abila Bose is one of the alumni, Kadambini Ganguly is another one, and now you move up and you find that Neena Gupta has received the Ramanujam Award for mathematics, and she is an alumni of that institution. So institutions have a big role to play in how women will contribute to society and so on.
Janaki Ammal was born in 1897 in Tillacheri, Kerala. After schooling in Tillacheri, she moved to Madras, where she obtained a bachelor's degree from Queen Mary's College and followed it up with an honours degree in botany from Presidency College in 1921. Under the influence of teachers at the Presidency College, Janaki Ammal acquired a lifelong passion for cytogenetics. Plant cytogenetics is a combination of cytology and genetics. Cytology deals with the study of cells, their origin, structure, function, and pathology of plants, and also as a means to diagnose or test for other diseases. However, genetics deals primarily with the patterns of inheritance of specific traits of the concerned plants.
IIT Kharagpur, India. With this brief introduction, so about Uttam sir is very good friend of mine, and he was actually left NASA position and he came to India. He is working in IIITB as a professor. So he is very humble and very good friend of mine. With this brief introduction about sir, and on behalf of KSTA and PG Studies, US Bangalore, and all of you, a warm welcome you sir taking this today's session.
Good morning, all of you. Sorry for the small delay. I live in electronic city, so took almost close to 2 hours to reach here. Although I took the nice road, but still got delayed. And thank you, Srinivas, for the elaborate introduction, which is not required actually. So we know each other for a very long time, maybe almost I think 15 or 20 years, and often meet at least 2 to 3 times in a year. Definitely, and I'm lucky that I'm able to accept and come always. So this time again, it was a he invited me only this month. He planned it for this training program and informed me just at the beginning of this month. So today I had a class in the institute, but I skipped it to so that I can attend this program. Already he told too much, so let's not talk about those things. So at the institute I am essentially teaching. Earlier I was used to teach data analytics, which is now discontinued, and currently I teach machine learning and jointly with another professor, and I teach database systems to BTech third year students and GIS to MTech second year students, and recently I started teaching a new course on spatial computing, which is altogether a new course, not at least being offered in any institute in India right now. So it is the advanced GIS. My core area of research is spatial data analysis, which is more to do with, like, for example, Google Maps or satellite images, spatial data. So on these data, we try to analyze them by using different techniques from machine learning or statistical techniques, and we try to derive information so that it is helpful to the planners, decision makers, and so on. Okay, so that is my area of work. Currently, there are 6 PhD scholars working in under me, and they are in different stages of their PhD from 5th year to 1st year, and 2 MS people already graduated, Master of Science. One worked in the area of homomorphic encryption, where they do. Where they worked on homomorphic encryption, which is mostly used for encrypting data, and the other one worked on continual learning, which, if time permits, I will definitely try to give you an overview. Continual learning is an advanced topic currently in machine learning, and 15 MTech graduates have passed out in the last 2-3 years. They worked on different applied machine learning areas, and including, for example, use of drone in agriculture, trying to identify crops in agriculture farms from drone data, trying to see which are the healthy, diseased crops and healthy crops, and then pothole detection on the road, then mask detection on people's face during COVID times, and so on, different types of projects. Okay, so these are all the different areas where I currently work, and currently I have one MS student who is working on again, he is very much interested in agriculture domain, so he's trying to see how we can use GIS in agriculture sector trying to solve various problems. For example, trying to look at crop health, or estimating the yield from farmland, and then looking at any kind of a disease that has infected farmland. So what is the stage of the disease, and how to overcome that, etc. So these are some different allied areas that we are currently working on. Okay, so linear regression correlation is a topic which has lot of importance currently in respect to data science, and linear regression is often used when we are not sure about what type of machine learning algorithms will be really useful for a particular problem. Okay, correlation although is a kind of a matrix that allows us to see whether two variables are correlated, but linear regression has much wider application than we think of, simply because when we have no idea about how variables are related to each other, generally in cases of multiple variables, linear regression is one of the best techniques to get started with. Later on, when your results with linear regression are really useful, you can continue to build more robust models with advanced machine learning topics or deep learning topics. But at this point, practicing linear regression is one of the best choice among all the machine learning models. So before we proceed, I would like to know about your background and are you part of some ongoing course, or right now you are doing some research? Anybody who would like to talk about? Now, all of you are from different places in Karnataka or from the same place?
Different place but same university. We are all PhD graduates.
Final year, okay. Okay, so most of you are from University of Agriculture Sciences. All of you, okay, all of you. So one is here, one is in Dharwad.
All from GKVK, only Bangalore.
Oh, all from GKVK. Okay. Nobody is from outside Bangalore. Okay, and all of you are in different stages of the PhD. All third year PhD. Okay, so I do not know. Sorry for that. How is the PhD carried out in GKVK? So is it like first year of the program goes with some courses that you have to do, and then subsequently appear for a comprehensive exam, and then you are allowed to start your research? Okay, the similar way. So all of you have already completed the coursework, this comprehensive examination, and you are in the middle of your research. Okay, so what are the kind of courses generally people take in first year? General courses. Are there courses on statistics, machine learning? No. So basic statistics, time series data analysis, these are there. Okay. So have you got a chance to learn linear regression earlier? Everyone has already learned. Okay. So then what do I teach? Huh?
Only some departments have statistics.
Oh, only few departments have studied. Okay, I had been to GKVK 2 years back for a lecture, whole day lecture. So, but I think it was statistics department. I am not able to recall. So I have not seen the whole campus. So I don't know how many departments are there, how they are distributed. But okay, some of you have already learned. So I hope this will be not too boring for you, for those who have already learned. For people who have not learned, this will be not too advanced, but it will give you an overview of what is linear regression and how do people use it. Okay, then the subsequent part we will try to cover logistic regression. Okay, and I have sample data. I don't have original data, sorry about that. You people are sitting on gold mine, so you have so much data to work on, and we people are data hungry. So we have to cook data, prepare data for all these experiments. So I don't have a real-time data, but some dummy data to show you how do we build models in R, and you can replace those data with your own data and try to see how will this work on your data. Okay, I have tried multiple times to collaborate with GKVK US to get some agriculture data, but not succeeded till now. Hopefully some day it will succeed and we'll get lot of agriculture related data to work on. Okay, so this part, linear regression, we will try to cover in 1 hour or 1 hour 15 minutes or so, and then subsequently we will also cover logistic regression. Okay, and then I will show you some codes. So I have sample data and written codes with comments on what is the meaning of each line in the code, okay, as a comment, so you can read that and execute it. I will show you some part in the class itself. about linear regression, multiple linear regression. Logistic regression I will just go through, and what you can do is take the code, and after the today's program you can try executing yourself. Okay, it's well documented. So each line I have put comments to indicate what this line will give you once you execute that line. Okay, so maybe either you can do it right away when I do, or you can take all the data and code with you, and you can do it at your own time whenever you feel you want to carry out that. Okay. So let's get started with the theory part. Okay, and in this part we are going to mostly cover linear regression and multiple linear regression, and correlation coefficient R square and adjusted R square. So people who have already learned these techniques, they will also agree that this is a very important topic, and very often you will encounter these terms in many research papers, especially for us who do research related to PhD work or for related to publication. So in most of the papers we encounter words like correlation, R square, statistical test, etc., and therefore this has very wider application. So let's begin with a very small introduction to the topic. Okay, so I will bring in a new term called relationship here. Okay, and slowly we will try to get into detail of linear regression. Okay, so the talking about the term relationship, the question that emerges is how do you describe relationship between things. Okay, for example, if there are two quantities, so the question would be, does knowledge of one quantity help to predict the value of other? Okay, so let's see an example. So is there a relationship between two numbers that appear when two dice are tossed? You have to answer. Is there a relationship between two numbers that appear when two dice are tossed? No, right? Probably not. Okay. Is there a relationship between the number on the top of a dice and the number on the bottom of a dice? Yes. Okay. Is there a relationship between the area of a state and its population? Maybe. Maybe if there is a rule that the population density has to be below this, then this will be true. Otherwise the city will become very crowded. Okay, right. Then is there a relationship between a state's population and its electoral vote? Yes. Okay, so what do we see is that taking the example of a dice, or taking the example of a population, etc., or electoral vote, etc., we were trying to see if there are two things, for example, two dice or population and electoral vote, are they in any way related or not? So for example, we looked at the we looked at a condition when there were two dice. Okay, and we saw that there is perfectly no relationship between the outcome when you throw two dice at a time. Okay, so in that context, let me slightly deviate for a few minutes, 5 minutes, and then we'll come back to the topic again. So the reason for deviation is that I wanted to introduce a new term right now in this context called a random variable. Who knows what is a random variable? What is a random variable? Okay, so we are going to define right now what is a random variable, and then bring again those experiments back for discussion. Okay, so let capital letter X be a random variable, okay, that can take the value that appears on the first die. Okay, and let Y be another variable, take the value that appears on the second dice. Okay, so therefore there will be a total of 36 possible outcomes when you throw two dice, X and Y. Okay, now I will introduce the word random variable at this point in time. Okay, and then we will continue our discussion further on the dice problem. So what is a random variable? A random variable is actually a function. A random variable is actually a function that assigns a real number, to each outcome, in the sample space of a random experiment. Okay, this is the simplest definition I have found in the book. Okay, a random variable is a function that assigns a real number, okay, to each outcome in the sample space of a random experiment. What is a random experiment? A random experiment is an experiment that can result in different outcomes, even though you repeat the experiment in a similar way every time. Every time. Okay, so that is called a random experiment. So for example, tossing a coin, you will try to toss the coin in a similar way every time, but you might expect a different outcome every time. Okay, that is called a random experiment. So a random variable is actually denoted by a uppercase letter, for example X here, and once you have completed the experiment, or once your experiment is complete, for example throwing a dice or tossing a coin, the outcome or the measured value is denoted by a lowercase letter. So for example, for this case, if you can say X is equal to 70 milliampere is some value after the experiment. Okay, statistically people define random variable like this. So a random variable also denoted as small r dot v dot x is a function. Again, see that this is a more rigorous definition. The previous slide gave a simplistic definition. This is a more rigorous statistical definition. So when you talk to people in statistics, they would like to explain you in this way. Okay, so we will not try to learn this particular definition, but just wanted to give you an idea as to what do statisticians explain when you try to learn random variable from them. So X is a function which maps the elements of the sample space big omega to the set of real numbers R. Okay, see that this is slightly different from the previous definition. So a random variable is a function which maps the elements of the sample space big omega to the set of real numbers R. Okay, so mathematically big omega will tend to R, that is a set of real numbers, and the range of random variable X is denoted by this X. So X is a variable because its value, that is X of omega. What is omega here? Omega here is a input, and the value of small omega will vary over the sample space big omega. Okay, and the value is random because the input itself is random. So let's take one example to make sense of what I am speaking right now. So consider the experiment of tossing a coin three times. Okay, so for this experiment, what will be big omega? What will be big omega? What is big omega? Big omega is your sample space. So sample space will be one of these outcomes or all these outcomes. Sample space is all these outcomes. So you are tossing a coin three times. So the outcome will be head, tail, head, tail, head, tail, head, tail, head, tail, head, tail, and tail, tail. All this is all the possible combinations in the sample space. Okay. Now let X of small omega. What is small omega? Small omega is one single outcome. Big omega is the sample space. Small omega is one single outcome is equal to, for example, assume that small omega is equal to number of heads in omega, which in word represents the number of heads that you see in three tosses. So what will be X? So X of 3 times H means H has occurred 3 times is equal to 3. X of tail, head, tail will be equal to 1. X of tail, tail will be equal to 0 because here you have no heads, only tails. What is the assumption? Assumption is that X of small, so we are assuming that let X of small omega is equal to number of heads. right? So number of heads can be either 3 or 2 or 1 or 0. Look at this sample space. Maximum number of heads that can occur is 3, minimum it can be 0 when there are 3 tails altogether, right? So your values of the random variable will be 0, 1, 2, 3 when you are interested in looking at the number of heads in 3 subsequent tosses. Okay. Okay, so now we have understood more or less what is a random variable. Now I am trying to bring one example, and all this explanation in the 2-3 slides from now onwards is trying to give you an overview how these terms will be useful in understanding that example. Okay, so let's look something at set theory. Okay, and see that we have a term called events. Events or in probability, not exactly set theory I'll bring here, but let me first introduce probability. In probability we have a notion of events. And then if there are two events, then we have something called intersection of events. We can have something called intersection of events. So let's say there are two events A and B. There are two events A and B. Then the joint probability of A and B is denoted as A intersection B. Okay, and A intersection B is the event consisting of all possible outcomes that will belong to both A and B. Okay, so now let's move on from intersection of events to contingency table. Okay, now I will put this intersection of events in contingency table in the next slide. So before that, let me introduce the term contingency table. Actually, contingency tables are those tables which are used to show probabilities or joint probabilities and marginal probabilities. Okay, so contingency table, see, I am first trying to introduce the concept of events and then concept of joint probability. Okay, now I want to place this joint probability in a table which is called a contingency table. Okay, why I am using joint probability? Because I have given one example of a dice, two dice being thrown together. Okay, and we saw that the outcome of the two dice is not at all connected, both are independent. Okay, but now I want to show the outcome of throwing two dice in a single table. That table is called contingency table. And what I will show in the contingency table is in the form of probability, essentially joint probability. Okay, so this is I am trying to connect slide by slide. Okay, so now see that joint probabilities arise in contingency table. And what is this table? Table is a the table lists the number of outcomes that correspond to each possible pairing of the first dice and second dice. Number of outcomes that corresponds to pairing of all possible pairing of the results of throwing two dice. Okay, so in a contingency table, in general, each row corresponds to value of one variable. Okay, and each column corresponds to value of second variable. What is the first variable here? First dice. What is the second variable here? Second dice. Okay, so now I am going to build a contingency table where I will try to show the joint effect of throwing two dice at a time. The rows indicate the first dice, column indicate the second dice. Okay, you can actually use I and J, I for the row and J for the column in the table to define the corresponding ith value and jth value in that contingency table. Okay, so let's see one example. So this is a survey example. Okay, so there is a survey of 100 adults. The following contingency table is derived. So this is the contingency table, an example of a contingency table. Okay, what this contingency table shows is it lists the joint probability. You know what is joint probability now. We have just touched events, then we looked into what is joint probability. See that we talked about intersection of events. Then we looked at what is joint probability, how is it represented in a contingency table, and now we are connecting all the concepts just we have learned in 3-4 slides with one example. Okay, this is a contingency table based on the outcome of a survey of 100 adults. Okay, so what it is showing is it is showing the joint probability of each combination of two variables. Okay, and the variables here are gender and type of smartphone they use. Okay, so people use either iPhone or Samsung or none of them. Okay, and this contingency table shows. So from the table you can see that if you pick up one respondent randomly, if you pick up one respondent randomly, and if M is the event that particular respondent is male, okay, and I is the event that the respondent owns an iPhone. See, there are two events. One is either the person is male or female. The other is either they hold iPhone or Samsung smartphone. Okay, two events, A and B. So if you pick up a random person, is an event that respondent is male, and I is the event that respondent owns an iPhone. Okay, then what will be probability of M intersection I? What is M intersection I? We just touched here, right? If A and B are two events, then joint probability of A and B is denoted as A intersection B. What are the A and B events here? A is gender, B is type of smartphone they are handling. Okay, so if you pick up a random person, and if M is the event that random person is male, and I is the event that he or she owns iPhone, then probability of M intersection I will be 16 out of 100. 16 out of 100. Okay, whereas probability that respondent is male will be 0.48. Will be 0.48, 48 divided by 100. Okay, and probability that that the smartphone is iPhone will be 0.36. Will be 0.36. Okay, so you got the example of a contingency table and how do we represent joint probabilities when there are two events A and B, right? Okay, let's now come back to the same example that we were discussing at the beginning. So I have two dice, okay, and this is the outcome of shown in the joint probability table of throwing two dice together. Okay, so Y is one dice, X is another dice, and see that each possibility has a joint probability of 1 by 36. Each possibility has a joint probability of 1 by 36. And look at the last column here and the last row here. It's 1 by 6. Okay, these are called the marginal probabilities of Y and marginal probabilities of X for the two dice problem. Okay, now let me show this outcome in the form of a picture. So I have dice 1, I have dice 2. The maximum number that can appear on each dice is 6. Okay, so look at the scatter plot. Look at the scatter plot of each outcome. Okay, what is the message I want to convey right now is, do you see any relationship here when you throw two dice at a time? The outcome of the two dice is shown in the picture here. Do you want to switch off this light if it is not visible clearly? I think the brightness is slightly low, right? This light we can switch off. Brightness is slightly lower. Is it better now? Okay, so what is this? This particular picture shows you the outcome while throwing two dice. Okay, now if this is a pictorial representation, do you see any relationship here between relationship between dice 1 and dice 2? We don't know what is the outcome. Outcome is as shown in the picture here. One of the outcome will be as shown something from the picture here. Okay, do you see any relationship in this particular picture? Anybody? Any relationship between dice 1 and dice 2? No. Why? Because knowledge of x, knowledge of dice 1 provides no help in predicting the value of y. So therefore, we are unable to find any relationship here. Okay. Now let us move to another example, related example. Let x be a random variable. You know now what is random variable. Okay. Which takes the value that appears on the top of a dice, and y take the value that appears on the bottom of a dice. Slightly different problem, but the same dice problem. Okay. How will the joint probability table look like? See, here we had dice 1, here we had outcome in the form of dice 1 and dice 2 on the row and column side. Okay, now you have only one dice. So how will the joint probability table look like? Will it look like something like this? What do you see? What do you see when you compare this to the previous table that we had seen earlier? Look at the joint probabilities value, and now look at the marginal probabilities value. Any difference do you see when you compare to the last table? What were the values for joint probability value in the previous case when you were throwing two dice? Right. So we see that marginal probabilities are same, but the joint probabilities here are different. So everyone got this idea of joint probability events, and how do we showcase or how do we show if two events are related to each other by looking at the joint probability table and by looking at the pictorial representation. Okay, now for this particular table I am going to show you the another pictorial representation. Okay, so this is the outcome, top of a dice, bottom of a dice. See how the values have been arranged. Compare this to the previous one. See, this was the earlier case. Throwing two dice, we could not see any pattern here. Okay, look at the case when you have only one dice and the outcome are top of a dice and bottom of a dice. Okay, do you see any relationship here? Do you see any relationship here? Yeah, intuitively we see, because we know that if 1 is at the bottom, 6 is on the top. Intuitively we know that this is going to be fixed, it will not change. So we can at least guess that yes, there is a relationship between top of a dice and bottom of a dice. Okay, there is a strong relationship because knowledge of x, knowledge of the top can be provided by knowing knowledge of can be guessed by knowing the value at the bottom, or vice versa. Right. So it says that knowledge of x can provide value of y. If you know one, you can tell the value of the other. If you know one side of the dice, you can tell the value of the other side of the dice. Okay. So we see that if you get this kind of a pattern, like we have seen earlier in this case here. Okay. So if you see this kind of a visual pattern, one way to understand if there is a pattern or not is by connecting these dots. Okay, certainly you can connect all these dots and you will see that you get a straight line. You will get a straight line from bottom left to top right. The straight line moving from bottom left to top right. Okay, and it will indicate that there is some relationship between x and y. X being bottom of a dice, y being top of a dice. Okay, so see, this is what I was trying to say. I am trying to connect all the dots with the help of a straight line. Okay, this branch of statistics or this branch of statistical analysis, where we try to fit lines, that represent a pattern of dots, is called regression analysis. See that in the previous example where we had so many dots, in this case, we cannot draw any line to fit which can touch all these points. It's not possible, right? But so it means that x and y are not at all related. Therefore, knowing the value of x will not help us in knowing the value of y. Okay, so it also means that for in linear regression, if there are two variables x and y, then they must be theoretically correlated, or else you will not be able to establish a relationship. Okay, we will revisit this point later on. So we see that here they are correlated. If I know one side of the dice, I can guess the other side of the dice, and hence I was able to get this kind of dots. Now certainly I can connect them. This study, this branch of statistical analysis, which involves fitting lines that represent a set of pattern of dots, okay, is called regression analysis. And henceforth, now we are going to explore how to fit lines in using an example. Okay, so before that, let's quickly bring another angle to this discussion and make sense of what we are doing here. So this is a broader picture. Okay, I am sure everyone might have already used these terms, listened to these terms earlier. This is a broader picture in the sense this is a kind of a machine learning technique, okay, which I have summarized. So machine learning techniques are broadly of two types. Okay, mostly the supervised techniques. One is classification, other is prediction. Okay, and see that linear regression comes under the category of prediction. I'm not saying forecasting, prediction. The word is prediction. Okay, the other part is called classification. So it is always advised that when you look up a problem statement, exactly try to figure out what has to be done. Okay, the question what has to be done will decide whether do you want to go for classification approach or prediction approach. Okay, so for example, I would say that let's develop an application where you have a camera, okay, and move the camera over plants, and there is the application that can quickly detect which leaves are infected by disease. So is it a classification problem or a prediction problem? We have to first be clear. Okay, this is a classification problem because you have been trained to analyze that if this is a leaf and you see black dots, it is a diseased leaf. Okay, if this is a leaf which is perfectly green, it is a healthy leaf. Okay, so you are doing some kind of a categorization. Black dots means diseased, no dots, green means healthy. So you are doing classification. Okay, so here in this example there is no role of prediction. So there is no point using linear regression. Okay, so what is classification? In classification, any algorithm you use, it will try to predict categorical class labels. Class labels can be healthy versus diseased. For example, in your Gmail, you might have seen you have separate categories, official, promotional, those kind of things, right? What are those? Those are categories. Those are categories in which your emails will automatically go and fit. So you can change the tab and see which are official email, personal email, and promotional email, and so on. So this is the typical classification problem. Okay, so in a classification problem, any algorithm will try to construct a model. Construct a model from where? Based on the data that we have collected from the ground, or based on the data that we have collected from the ground truth. And using this model, it will now try to classify new test cases. For example, if my model is ready, you give me a new leaf image. I will put my camera and it will detect it's a healthy versus diseased. So this new test case is called classification. So you now give me 10, 15 different types of leaves. I can tell you which one is healthy, which one is disease. My model can sometimes go wrong. I'm not saying that it will be 100% perfect. Maybe because it's not trained to learn certain types of diseases. But with the available training data, I will try to build a model that is robust enough to detect disease in different plants. This type of detection or email, for example, promotional, official, etc., they fall under the category of classification. Okay. In prediction, we try to model continuous valued function. See the word here, categorical class label. See the word here, continuous values function. So in prediction, we predict unknown or missing values. Linear regression is widely used. Linear regression is widely used to predict unknown or missing values. For example, I have rainfall data from 2000 to 2022. In between 2014, July data is missing because of some reason. The data entry person forgot to enter or some error value. I can use linear regression to predict that value, to predict that missing value. Okay. Although there are other methods also apart from linear regression which people can use. Simplest method is take the average of the before month and after month, means June and August. Take the average and fit it in between. Other methods are, for example, use the nearest neighbors and take the nearest neighbors and estimate what will be the value of the missing part. So k nearest neighbor algorithm is also used, but mostly people prefer linear regression. So linear regression is used to do prediction, and it is widely used when you have unknown or missing values to fill those things, to fill the unknown or missing values. Okay. Now this is a more broader picture. So in regression, I am generally in all the machine learning problems. So even when you use linear regression, you are using some kind of machine learning algorithm. Okay. So all these regression, prediction, they all come under machine learning. Okay. So regression, the output variable to be predicted is continuous, whereas in classification, the output variable to be predicted is categorical. Okay, as we saw in the last slide. So remember that in regression, the output to be predicted is continuous, whereas in classification, the output to be predicted is categorical. So by looking at the problem statement, you have to find out what will be the likely outcome that we expect. If it's a continuous variable, use regression. If it's a category A, B, C, healthy, diseased, etc., use classification. If there is no training data, if there is no ground truth available at all, okay, then go for the third set of technique called clustering. So in clustering, you have no ground truth, but we use one of the criteria, one of the attributes in the data itself to group the data points into smaller subgroups. These subgroups are called clusters. Clustering is a natural grouping of data based on some criteria. For example, people sitting in this room, I can group all of you based on various categories. First category could be based on gender. Okay, two classes, A and B. Second category could be based on the color of your t-shirt or clothes. White, I can fix 4 or 5 classes, white, blue, green, red, etc., and say that all of you must be aligned to one of the 5 classes. Okay, then I can group all of you, for example, based on your marks in the previous semesters or in the coursework. People who have got more than 80% will be one A, people with grade A, then people with lesser than 80, more than 70 will be grade A minus, and so on. So see that for the same population, I am trying to group all of you based on different criteria, different attributes. Age, I can even group based on age. For example, people from 20 to 25, 25 to 30, 30 to 35. Based on age, gender, color of your clothes, marks in the previous semester or term. So here I do not have any information about you, but from the available data, I am trying to group all of you into different groups called clusters. So this is the third set of technique that people use when ground truths are not available. Okay, so right now we are focusing on regression. So in order to solve a problem, so you have to first make out that where does your problem stand out? Do you need regression to solve it? Do you need classification to solve it? Do you need clustering to solve it? It's not that I know regression, so let's apply regression everywhere. It should not happen that. So we should know what is that you want from the data, accordingly select the right technique. So see that regression and classification, since they are based on ground truth data or training data, they are called supervised learning methods. So regression is a supervised learning method, whereas clustering has no ground truth, no training data, and therefore it comes under the unsupervised learning methods. Okay, so so why I'm explaining all this and taking your time is because next lecture will be on classification. We are going to learn logistic regression, which is not prediction. Logistic regression will help you to perform classification. Okay, and now you essentially know the difference between prediction and classification, right? So the name might appear similar, linear regression, logistic regression, but their purpose is different. One does prediction, other does classification. And in this session right now, we are focusing on prediction. Okay, so to summarize, in supervised methods you have regression, classification. Regression has a class label, classification also has class label. The type of label in regression is continuous, the type of label in classification is categorical. Logistic regression will give you categorical labels, not continuous labels. Okay, and in clustering you do not have a label, you just form groups, and then manually you have to label each of these groups. Okay, regression is the most commonly used predictive analysis model. Okay, so now you know the context where we should use regression. Okay, so see that how do we start defining regression. So if there are two variables which are significantly correlated, okay, and another important point, and there is some theoretical basis for doing so. If I say if there are two variables significantly correlated and there must be some theoretical basis for doing so, I will explain you this point in the next slide. What is meant by theoretical basis with an example. Okay, if there are two variables, then it is possible to predict value of one variable, such as top of a dice, from the other, such as from the other, that is bottom of a dice. So what I am saying, if there are two variables, it is possible to predict value of one variable, top of a dice, from other variable, which is bottom of the dice. Okay, this is known as regression analysis. So regression means estimation or prediction. Prediction of what? Prediction of unknown value of one variable from the known value of other variable. That is, maybe the unknown value will be bottom of a dice and known value will be top of a dice. Okay, now you can extend this concept for different types of applications, and top of a dice, bottom of a dice is just an example, but you will be able to connect it to different applications. Okay, what is the use of regression? It is used to establish a linear relationship between continuous variables, also called predictor variable or explanatory variable or independent variable, and so this is actually x, and response variable, which is y. It is also called dependent variable, and this is done using a straight line. Okay, another important point to emphasize is that regression guarantees interpolation but not necessarily extrapolation. What does it mean? Anybody who would like to tell one line about the last bullet? Linear regression guarantees interpolation but not necessarily extrapolation. What is interpolation? I am sure you will know what is interpolation. You don't have to be exactly defining the term, but roughly what is meant by interpolation with some example. Generating, to give a very simple example so that everyone can understand. Interpolation. Yeah, he is closer to the right answer, very much close. So let me give you one simple example. Suppose that we all live in this city. It has become huge because of the growth of the city, urban sprawl, urbanization. So let's talk about weather stations. Okay, so we know that if we represent the city temperature by one weather station, it will be wrong, because for example GKVK campus or IISC campus, they have lots of trees, so generally the temperature is lower here. And if you take the temperature of MG Road and generalize saying that entire Bangalore city is hot, it's not true, right? So you may have, let's say, 20-25 weather stations in different wards, 20-25 weather stations in different wards across the city. Okay, now now see that it's not there are currently 200 wards, I think 200, 199 or 200 wards. It's not possible to have 200 weather stations in all the wards. Okay, so what government can do is maybe install 20-25 weather stations evenly distributed in the whole city. Okay, now what okay, 25 wards are covered. What about remaining 175 wards or 174 wards? There are no weather stations. Okay, so what we do is, from the available 25 values from 25 weather stations, we will try to guess or estimate the corresponding values for other wards. Okay, for example, take temperature. So there will be a weather station in this campus, but may not be in Thanisandra, which is closer to the road. Okay, so and let's say the second weather station is in Hebal. So we will use these two weather stations to estimate the value of temperature in the nearby location Thanisandra. Okay, likewise we will use 25 values from 25 weather stations across the city to estimate the value of temperature for all 200 wards in the city. Okay, so we use interpolation a lot when the data are not available uniformly for all places, and it's not practical. For example, suppose that it is a terrain where we cannot easily reach, a valley, mountain, and that sort of thing. So what do? We'll pick up some samples. We'll pick up some samples and we will try to do interpolation. That is, okay. Let me not connect to that idea. Let me give another example with a diagram. You may already have heard about the term contours. You know what is a contour? Contour lines. Contour lines are iso lines that represent similar height above mean sea level. Okay, so for example, a contour line could be like this, and it might show 200 value, means 200 meter above mean sea level. Okay, then another contour may be something like this, and this might show 180, means 180 meters above mean sea level. So all those points, all those locations that fall on this line will have 180 meters elevation above mean sea level. Okay, similarly I can have third line that may be 160 meters above mean sea level. Okay, now what happens to places which are between 160 and 180 or 180 and 200? See, there is a 20 meter gap here, 20 meters gap. What happens to places which are between that, which are between 180 to 160 or 180 to 200? We have no idea about those places. 20 meters is a huge distance, right? Also for elevation, 20 meter elevation is too much. So how do we guess values for those places? So what we do is we use something like interpolation to interpolate or find out values between values of height in this region. Okay, this is a very nice example of how people use interpolation to find out height of those places for which you do not know the value, and you use the nearest points, nearest values to interpolate. Okay, so likewise we can estimate height for any place in the world using interpolation. Okay, So regression is used regression is used in interpolation. That means you have value 180 and 200 meters of a mean sea level. You can use regression to find out or estimate the value 190. But you cannot use it to extrapolate. So if I say that I have a rainfall data from 2000 to 2022, I cannot use regression to find out the value of rainfall in 2024. You can try that, but because you do not know the behavior of rainfall in the coming days, your prediction can be wrong. Okay, what people do for such things is to do forecasting. That's why people use the term weather forecasting. People never say weather prediction, weather forecasting, right? So in forecasting, we don't use these prediction techniques. We use time series modeling techniques like ARIMA, auto-regressive integrated moving average, or ARMA. And people have now started using deep learning techniques also for forecasting. That is what is going to happen in future. So see that regression is used to estimate something in a range, in a given range of values, whereas time series forecasting is used to extrapolate. There is a difference. Okay. So I had at some point of time insisted that there has to be some theoretical basis for connecting the two variables x and y. Okay, see this example. There is an observer. Okay, observer sees that it's raining, and observer also sees that everyone is carrying umbrella. So what observer understood that if people have an umbrella, they can bring rain. So what this is how they connected it. See, the observer saw that it's raining and people are carrying umbrella. Okay, so I'm saying that this observer doesn't know the theory of how rainfall occurs, etc. So the observer could connect that. Okay, if there is an umbrella, they can bring rain. Okay, and the observer takes the umbrella and says make it rain. But see that umbrella and rain, they are used together, but they are not correlated. There is no theory to connect on that. There is no theoretical basis. So this is a correlation, but it's not a causation. Correlation does not cause causation. Umbrella will never bring rain, although rain and umbrella are correlated. Okay, so therefore in regression we have to ensure that that there is some theory to connect the two variables x and y. Okay, assume that x is rainfall, y is umbrella. So they are correlated, but one doesn't cause the other. Umbrella doesn't cause rain. So then regression may not work here, or give you a wrong prediction. Okay, so we will proceed after a small tea break. Okay.
ಇಲ್ಲೊಂದು ಶೀಟ್ ಸರ್ಕ್ಯುಲೇಟ್ ಆಗ್ತಾ ಇದೆ, ನಿಮ್ಮ ಹೆಸರೆಲ್ಲ ಕರೆಕ್ಟಾಗಿದೆಯಾ, ನಿಮ್ಮ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಸರಿ ಇದೆಯಾ ಅಂತ ಒಂದು ಸರಿ ಚೆಕ್ ಮಾಡಿಬಿಡಿ. ಸರ್ಟಿಫಿಕೇಟ್ just check it, your name is right or wrong, and your department name also.
Okay, shall we continue? Okay. So this is a scatter plot of two variables. For example, x-axis is the marketing budget in some unit, for example in lakhs, which is an independent variable, and y-axis is sales in crores. Okay, and this is a scatter plot where sales is a dependent variable. Okay, so we actually start building a linear regression model with a simple plot. Okay, and this is a simple scatter plot to get started. So now we move ahead and revise our old concept of equation of a line, which is given as y is equal to a plus bx, where b is the slope, delta y by delta x, and a is the y-intercept. So in order to write the equation of the line, we need two information. One is the slope, other is the y-intercept, which is actually a constant term, a. Okay, so how do we express linear regression mathematically? So for a population where y is my dependent variable and x is my independent variable. Okay, so imagine that we have one independent variable only at this point of time. For a population, we represent it as yi is equal to beta 0 plus beta 1 xi plus e. Okay, what is beta 0 here? Beta 0 here is the y-intercept, the constant term. Okay, and beta 1 is the coefficient, and both beta 0 and beta 1 we are going to determine from the data. So this applies for a population, and where beta 0 and beta 1 are the population parameters, and from these parameters we will try to estimate the value of y. Okay, so given values of x. For a sample, we express the same equation of a line using yi tilde is equal to beta b0 plus b1 xi plus ei. Ei here is the error parameter. Okay, and this is a sample this is a for a sample, this is an equation that is used for prediction. Okay, so this is for a population and this is for a sample. There is no much there is no difference at all, both are exactly same, but only the choice of notations that we have used for beta 0 and beta 1 and y and x are different and the error term. The EI term that we see here is actually the error term. We will come to each of these terms separately after some time. Okay. Now see that we are going to use these equations to in linear regression to model a set of data, maybe a sample of data. Okay. Now see that let's go back to the previous example of marketing budget in x-axis, which is my x variable, and sales in y variable. Okay, so what is the idea? Idea is that if you spend more in marketing, you might end up having more sales. Okay, so if you advertise for example in newspaper, radio, mobile websites, then your sales might go up because more and more people will watch your advertisement and try to use your product. Okay, so see that budget is independent. The amount in budget is independent. It's up to you how much you want to spend, and and see that depending upon how much you want to spend in marketing, sales can increase or decrease. Okay, so see that in some sense budget is an independent variable, marketing budget is an independent variable, and sales, which is dependent on marketing, is a dependent variable. Okay, now we had sales is a dependent variable, so we had this data, this particular graph we had seen earlier. Now what we want is to draw a line that can connect as many points as possible, because I want to use this line, I want to use this drawn line to show the distribution of these red dots. Okay, so let's say I draw one line here, another line here, another line here. Okay, so I have drawn 3 lines. I can actually go on and I can draw many lines, trying to connect as much points as possible in every attempt. Okay, so we have drawn 3 lines. Now the question is, I have drawn 3 lines, trying to connect as many points as possible in each line, but which of these lines is the best? Okay, which of these lines is the best? So the idea is that, or the message is that, however best you try, you will always have some deviation from the points in all the lines. You cannot draw a perfect straight line that will connect all the points. Always the line will have some deviation from some of the points. So for example, this is a deviation, this is a deviation, this is a deviation, this is a deviation. Okay, so even in the best possible line, you might have some deviation. So what we try to do is, we try to draw a line connecting all the points in such a way so that this deviation is minimized. This deviation is minimized, and this deviation is actually the error. Okay, so now we will talk about the error. We will talk about the error term. So why it is error? Because I wanted to draw a line that can see what I am trying to say. People are sitting in this room. I want to draw a straight line that can connect everyone, but that's not possible. If I draw a line like this, most people sitting in this corner and that corner will not be connected. If I draw a line like this, then people in that side will not be connected. So the point here is that I can never draw a straight line that can connect all of you. Okay, so the best idea will be, draw a line that can minimize your deviations from the line, minimize your deviations from that particular line. Okay, so these deviations are called errors, and in statistical terms they are called residuals. Okay, so the total, the overall error is called SST, or in short it is called SST, which stands for total sum of square. total sum of square. Okay, total sum of square is equal to sum of two errors. One is SSR, okay, which is sum of square due to regression, and other is SSE, sum of square due to residual or error. Sum of square due to residual or error. This error is due to regression, this error is due to regression, and this error is due to the error term EI, what we have seen in the equation, earlier equation here. This error term, this EI is the error term. Epsilon in the for population and small EI for the sample. Okay, so now see that the total sum of square is equal to sum of square due to regression plus sum of square due to residual or error, that is small EI term. Okay, let's now intuitively try to think where are these errors in the plot, okay. So see that this is a plot, and SST, that is total sum of square, is equal to yi minus yi hat. Okay, let me write here something. So see that y is equal to beta 0 plus beta 1 x plus e term, right? This is the line of the equation which we have also learned in school, line of equation, right? Now see that there are multiple observations of y, y1, y2, y3 and so on, y1, y2, y3, yi and so on, yn. Okay, now yi is my ith observation of y. Okay, so what is SST? That is total sum of square. Okay, now this is my y observation, and assume that the average value of all this y, I denote it by y bar. Average value of all this y, I denote it by y bar. Okay, and also the estimated value from linear regression model that we will get, I will denote it by hat, by symbol hat. y2, for y2 estimated will be y2 hat, and so on. Okay, now I am going to use these symbols, especially y hat and y bar, to explain the error term. Okay, total sum of square, SS or SST, in some books they write TSS also, total sum of square. Sometimes in some books they will write SST. This is equal to yi, that is take one observation of y, take one first observation of y here, this observation. Okay, y1 minus y bar, that is this. So what I want to see how much is my first value of y deviating from the average of y. How much is my first observation of y deviating from the average of y. Y bar is equal to, what is y bar? Y bar is equal to y1 plus y2 plus so on till yn divided by n, average of all that. Okay, so in SST I am trying to see individually how much each observation of y is deviating from its average, and then summing it up here. Okay, so in some sense this is the overall deviation of each y from the average. Okay, this is your SST. Okay, now let's come to the right side here. SSE, which is sum of square due to error. What is that? What is the error? Error is yi minus yi hat. What is yi hat? Yi hat is the predicted value from the model, and yi is my actual value. Okay, so actual value is 1, predicted can be 1.1. So what is the error? Error will be 1.1 minus 1 the whole square, or you can say 1 minus 1.1 the whole square. Since you are squaring it, the effect of negative sign will go. Okay, so you sum this for all the observations, y1, y2, y3 and so on, for all the estimated value from the model that is shown by yi hat. Okay, sum it up. That is called the error, means the model error. How much on an average the model has produced error for all the I observations or n observations. Okay, so this is my sum of a square due to error in each observation y1, y2, y3, y4 compared to y1 hat, which is my estimate from the model, y2 hat which is my estimate from the model, yi hat. I hat symbol is used to show the estimated value from the model. Okay, so this will also tell us how good is the model in actual prediction. SSR, which is sum of square due to regression, is equal to estimated value, is equal to the deviation of the estimated value from the average. See, here we were also doing the same thing, but for the actual observation deviation from the average, here we are trying to see how much is the estimated value deviating from the average. How much is the estimated value from the model deviating from the average. So now see that SST is equal to SSE plus SSR, that is your deviation of each y from the estimation, from the estimated value from the model, and this is deviation of each estimated value from the average of all y. These two together form SST, which is total sum of square. Okay, let's try to see now mathematically what we are talking about. So I have observation 1, 2, 3, 4, n. Okay, then for n observations I have y to yn values, x to xn values. Okay, now total deviation is equal to yi minus y bar. Y bar is your average of y. Okay, yi minus y bar. So you do this summation for all the y observations, which is your SST, is equal to deviation due to regression, that is yi hat minus y bar, which is deviation of each estimated value of y from average of y, plus e term. What is e? What is e now here? SSE. What is SSE? What deviation? What deviation? See, this is my actual observation. This is my model observation. Okay, so both should be actually equal. If my model is perfect, both values should be equal. But if this is slightly deviating, that deviation is your EI term here, error. Okay, so see that you sum it all for all the observations, n observations, and you get SSE. SST, total sum of square, is equal to summation of SSR, sum of square due to regression, plus sum of square due to residual, also the EI term. Okay, let me explain in one more way what we are talking about. See, our so this error term is also called residuals. Is also called residual. See, what I am saying is that look at the points here. Here, each of these points are deviating by some amount from the straight line. Deviating by some amount from the straight line. Okay. Now see that the error term is if you use this line equation to predict the value of these blue ones, okay, then it will not happen that this line equation will give you the exact value of these blue dots. There will be some deviation always, because I cannot have a perfect model. This deviation is captured here. EI is equal to yi minus y predicted from the model. Okay, and our goal is to minimize. Look at the arrow going downwards. I want to minimize this e1 square plus e2 square and so on plus en square. Okay, this is sum of square due to error, and I want to minimize it. I want to draw a straight line in such a way so that this deviation is minimized for all possible points. Okay, so see that I can also rewrite SSE as the difference of y minus beta 0 minus beta 1 x and square it for all the terms. And what I get is here SSE is equal to yi minus beta 0 minus beta 1 x. So what is this term? This is our what? Beta 0 minus beta. From where did it come? Can I move this term on the left hand side, this term, and know the error? See, let me erase. See, actually this is the ideal case. This is the ideal case. Okay, but I need to add some error term, because this is never going to happen. I will never have a perfect line that can predict all points nicely. So I will have some error term here. Okay, in order to know the error term, if I shift this on the left side, that is y minus beta 0 minus beta 1 x, will I get the error term? Okay, so this is the error term, and I have now summed it for all the n observations, squared it and summed it for all the observations. This is my SSE, sum of square due to error. Okay, and I would like to minimize it as much as possible, Okay, so now we can get the equation of best fit line, by minimizing this SSE, sum of square due to error. And how do we minimize it? There are methods from linear algebra called ordinary least square, and there are methods from calculus called differentiation, and there are methods from optimization called gradient descent method. So using ordinary least square, we can minimize the error as much as possible. Where have you learned ordinary least square in school? We have learned ordinary least square. Any example? Yes. Ordinary least square. Least square problem we have already learned in school. It's not a totally new concept. Not LCM. Recall what is ordinary least square. Okay, I will leave for the time being. I will ask this question again after lunch. Let me see how many of you can recall. Ordinary least square, OLS. It's very popular method in schools. I think 8th, 9th we study all this. Okay. So this error is minimized by using ordinary least square. Ordinary least square uses differentiation followed by the gradient descent method. Okay, let's not worry about differentiation and gradient descent method right now, because our focus is something different. Let's now not go into that direction. But idea is that we try to minimize the error as much as possible so that we get the perfect or best fit line that can minimize the deviations. Okay, so now what do you get by doing all this? Ask these two questions to our own self. How does the best fit line represent the scatter plot? See, this is what we began our discussion, that however best you try, you will always have some deviations. We cannot have a perfect line touching all the points. So my question is, after doing all this, how best does the best fit line represent that scatter plot? Okay, and how well does the best fit line predict new data? We are doing all this for prediction. Remember, linear regression is used for prediction. So we are doing all this for prediction. How best does your best fit line, as what you have defined, how best does it predict the new data, new value, that is estimated value? Okay, so this is all about linear regression, what we do, what we minimize, and what we try to achieve. Okay, now let's move into, before we get into trying to discuss more related aspects, let's see some of the assumptions that must be valid while doing linear regression. Okay, these are 5 assumptions. We cannot afford to ignore it, especially because in our data sets, agriculture data sets, plant data sets, people are very particular about putting all the statistical details in their paper. What p-value, significance, correlation, etc. So we cannot, we may not have to explicitly write this in the paper, in our paper that you want to submit as part of your research. We may not have to write all this in the paper saying that we have done all the tests and all the assumptions are valid. It is already in some sense understood that if you have used regression, your assumptions are already fulfilled. We don't write that we did linear relationship test, multivariate normality test, and all are proved to be true. We don't do that. So we believe that these assumptions are automatically valid because you have done it as part of your linear regression. Okay, but as a customary, we should know that these are the assumptions that must be validated for any linear regression problem. Okay, what are those assumptions? Linear relationship. See, linear relationship means what is the goal of linear relationship? We want to build a relationship that is linear in nature between x and y. If that relationship doesn't exist, what do we build? Nothing. We cannot build, right? So inherently in the data, that relationship should be there. Inherently in the data, that relation should be there. If it's not there, then we cannot build at all. Okay, so this is one of the assumption. Second one is multivariate normality. Third one is no or little multicollinearity. Fourth is no autocorrelation, and fifth is homoscedasticity. Okay, so these are the 5 assumptions. So let's now see each one of them in the next few slides. Okay, so first one is linear relationship. So we know that linear regression needs some kind of a relationship to be there between the x and y, dependent and independent. Okay, linear relationship assumes that there is some relationship between x and y, and also assumes that this relationship is linear. So before you proceed with linear relationship, please check if your data is linearly distributed or not. Okay, so also we need to see if there is an outlier in the data, because linear regression itself is sensitive to outliers. Okay, so how do you check linearity assumption? Best way is to just draw a scatter plot. Okay, see that this is perfectly linear, no doubt, and the first case is non-linear. I cannot build any linear model on this data. There is no pattern. What do you build? How do you draw a straight line? Right? So this assumption can be validated right away by just plotting the data. Remember the sales and marketing budget and sales, there were dots in some pattern. So we could at least know that they can fall in close to straight line, not exactly straight line, but here there is no pattern at all. But here there is a pattern. So this is the first test. Okay. Second test is multivariate normality, which means that all variables which are involved in linear regression must be multivariate normal. All variables involved in linear regression must be multivariate normal. Okay, and this assumption of multivariate normality can be checked in several ways. There are several ways. Okay, easiest way is the QQ plot. What is the QQ plot? Quantile plot. Quantile plot. I think it's a theoretical quantile versus the quantile of your data. So I will talk about this again in the next slide. Then there are very strict statistical tests in already existing, and I think there are 5 tests I have not mentioned here. These are 5 normality tests that you can use to check whether your data are normal or not. One of the tests is Kolmogorov-Smirnov test. There are 5 other tests I have not put here, but some people use all 5 tests. Some people use 1 or 2 tests and conclude that okay, data are multivariate normal. So this is a plotting way. I mean, this is just a exploration way. You just plot this QQ plot and see. But this is a more strict test. Kolmogorov-Smirnov test. This is more strict test. This is a statistical test. If your data are not normally distributed, okay, then some kind of a non-linear transformation such as log transformation will fix that. So you can try attempting some log transformation on the data which will make it linear. Okay. So this is a symmetric curve which also shows that data are normal. Symmetric bell-shaped curve. You already know about bell-shaped curve, right? So this is one example where you have a data and the plot shows that it's a bell-shaped curve, hence it is normally distributed. but we must go for a more strict statistical test. Okay, in many places they definitely advise, but people tend to ignore it. I mean, they assume that okay, my data will be normal, so let's not worry about it. Okay, what is a QQ plot? So this is an example of a QQ plot on the top left. Okay, it is a graph. It is a graph of quantiles, sample quantiles and quantiles of normal distribution. It is a graph of sample quantiles and quantiles of normal distribution. So if our sample data are actually normal, okay, then the sample quantile and theoretical quantile will match and it will follow a linear trend, something like this. So this is normally distributed, this is not normally distributed. You can make out. Okay, so this tells us about QQ plot is easy to draw in R. It's not at all difficult. There is a ready-made command and then input variables and it will plot and give it to you. Okay, so this shows normality, this doesn't show normality. So what all we have covered? We covered linear relationship, multivariate normality. Okay, next we will go to multicollinearity. Little or no multicollinearity. So linear regression assumes that there is little or no multicollinearity in the data. Okay, when does multicollinearity occur? Multicollinearity occur when the independent variables, that is your x1, x2, x3. See, what we are learning right now is f is a function of x1, x2, x3 and so on. Okay, so all these independent variables, they should not be correlated to each other. Okay, so multicollinearity occurs when these x1, x2, x3 are highly correlated with each other. Highly correlated with each other. What it means is that information that is present in x2 is also present in x3. So it is actually a kind of redundant information. We can try to remove one of them. So you, for example, for your problem, you might have collected 10 variables. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Later on you observe that variable number 2 and variable number 6 almost telling the same thing. It's a repetition. So you can remove, because variable number 2 and 6 shows the case of multicollinearity. Information is repeated. So there is no need to include all the 10 variables in your model, because 9 variables can also give the same result. So remove one of the variables. Okay. How do you test multicollinearity? There are few easy ways. Okay. First is correlation matrix. Correlation matrix. So you try to compute correlation between independent variables. Okay, and if the correlation coefficient is smaller, then they are not correlated. But if the coefficient correlation are close to 1, then they are correlated. So we can remove one of them. Okay, so one way to reduce the number of variables is just compute the correlation matrix among all the variables. Anybody who would like to give an input, how will the correlation matrix look like? Suppose if there are two variables, two independent variables, x1 and x2. Okay, so you compute a correlation matrix between x1 and x2. How will it look like? Yes. Two variables, so will it not look like something like 2 by 2 matrix? 2 by 2 matrix. So your correlation from x1 to x1 will be 1. And correlation from x2 to x2 will be 1. Diagonal elements will be 1. Non-diagonal elements will give you the correlation between x1 and x2. If they are highly correlated, you can safely ignore x2. Just keep x1 in the model. Okay. Other way to check collinearity is used something called VIF, various inflation factor. Okay. So various inflation factor is reported to you by our software. I will show you later on when we do hands-on. And if VIF value is more than 5, so it may indicate that there is a multicollinearity. So you can safely remove that variable. Okay. People also use tolerance and condition index to check multicollinearity, but I think correlation and various inflation factor are sufficient for most of the problems. Okay. if multicollinearity is found in the data, how do we overcome it? Centering the data, that is, you subtract mean of variable from each score. Okay, this will help to solve that problem. Remove multicollinearity. Okay, or remove that independent variable itself that have high variance inflation factor values more than 5. Okay, so we have now covered multicollinearity. Next is autocorrelation, or the assumption is that in linear regression data should not be autocorrelated, or there should be no autocorrelation. So linear regression requires that there is little or no autocorrelation in the data. No autocorrelation in data. When does autocorrelation arise? Autocorrelation arises or occurs when the residuals are not independent from each other. When the residuals are not, what is residual? E1, E2, E3, remember the term. Y is equal to beta 0 plus beta 1 x plus E. E1, E2, E3, these are residuals. So linear regression assumes that there is little or no autocorrelation in the data. Autocorrelation occurs when these E1, E2, E3 and so on are not independent from each other, but they are dependent on each other. Okay, how do we check for autocorrelation? So there is a popular test called Durbin-Watson test. This Durbin-Watson D test will test whether a data has autocorrelation or not. So the null hypothesis will be that residuals are not linearly autocorrelated. So you can use this test and find out. Okay. Then the fifth assumption is homoscedasticity. What it means? Homoscedasticity means the residuals are equal across the regression line. The residuals are equal across the residual line. Again, I am talking about E1, E2, E and so on. Okay, so it describes a situation in which the error term, and often the error term is referred to as the noise or any disturbance in the relationship between dependent and independent variable is same across the values of the independent variables. Okay, so linear regression assumes that the data are homoscedastic. Linear regression assumes that the data follow homoscedasticity. Okay, so that is variance of the residual or error term is constant. Variance is constant, that is, it is same across the independent variables. And how do you come to know about this? So you can again use a scatter plot of residuals, to find out whether the data follow homoscedasticity or not. Okay, so see this example. So this is an example where you see red dots in the first box, blue dots in the second box, and green dots in the third box. Okay, there should be no clear pattern in these distributions. And if there is a pattern, data are heteroscedasticity. Okay, so see that here there is no definite pattern. That is the variance is constant among the residuals, whereas in this case you see there is a pattern of dots, and what this pattern dot shows is that the error increase and then decrease. Okay, and this violates the assumption of constant variance rule. Okay, again here in this example, see that there is a specific pattern of errors, the dots. So here the error decrease with the predicted value depicting heteroscedasticity. Okay, there is a strict statistical test called Goldfeld-Quant test, and it can be used to test for heteroscedasticity. What this test will do is it will split the data into two groups to see if the variances of the residuals are similar in the first group and the second group or not. Okay, So these are the 5 assumptions. Let's again go back and recollect. What are the 5 assumptions? Linear relationship between x and y, multivariate normality, data should be multivariate normal, little or no multicollinearity. What is multicollinearity? Independent variables should not be correlated, no autocorrelation, and 5th one is homoscedasticity. Okay, so we have completed the assumptions. Now let's take one toy example and compute manually the regression equation. Okay, so I have very small data with with just 12 observations, month on from January to December, and number of hours of sunshine and millimeter of rainfall. Okay, and hours of sunshine is independent variable, millimeter of rainfall is dependent variable. Okay, so I would like to compute regression equation y is equal to b plus ax. Okay, so b is computed here, and all the summation x y, summation x, summation y are already calculated from the tabular data. Okay, so we just substitute here and get the value of slope, which is 0.595. Then we go ahead and compute the value of intercept. Okay, intercept, so intercept a is equal to y bar minus bx bar, and this turns out to be from this tabular data, this turns out to be 6.695, which is the intercept. Okay, and a regression equation will be y is equal to 6.695, which is a constant, plus slope into x. That is a regression equation connecting hours of sunshine and millimeter of rainfall, where millimeter of rainfall is a dependent variable, hours of sunshine is an independent variable. So this was a easy problem because there are only 12 observations, small data, so you can even do this in Excel sheet. Okay, but very often the data will be large, and then doing this manual calculation will be too difficult, so we will depend on some software to do this. So there are software modules in R that can help us to do this. Even Excel has functionalities that can help you to build regression line along with the R square value. Okay, so now I just mentioned about R square value, and now we will see what is R square value. So we will do a hands-on about how to get this equation in R later on once we complete the theory part. Another important term that you will often read in paper is R square. Okay, R square or capital R square, and or sometimes you just read in the paper as R squared, the word is written. It is actually the coefficient of determination. It is also called the coefficient of determination. Okay, why is the need to learn this topic? Why do we need to know R square? Good, because you have built a model, linear regression model, you have built you have come with an equation of a straight line, and you say that this particular equation is good enough for prediction. Okay, but I want a measure to see how good is your baseline. How good is your baseline? Is it really perfect or is it close to excellent, and so on. Okay, so this R squared measure or R square value will tell us how good is your model. Okay, so when you perform linear regression either in Microsoft Excel or R or any software, it will also report you R square value. R square value, and R square value is generally between 0 to 1. Okay, if it is 1, it means that all the observations fit in a straight line. If R square value is 1, it means that all the observations, the dots, they fit in a straight line. If it is 0, it means x and y are completely independent, so linear regression will not work at all because x and y are not at all related. Okay, so what does R square give you? R square gives you the percent variation in y that can be explained in x. Percent variation in y that can be explained in s, but that can be explained by x. Okay, percent variation in y, that can be explained in x. Okay. Now we have seen regression, and we have seen r squared value, which is the coefficient of determination. Now we are going to learn another term called correlation. Correlation. At this point, it will be good to compare what is correlation and regression theoretically. Okay, with an example. So when you these two terms are often used in while reporting the results in paper or in report. Okay, but what does it mean? How do they differ? So the goal of correlation is to see whether two variables co-vary. The goal of correlation is to see whether two variables co-vary. Okay, and it is used to quantify the strength of linear relationship, and it is used to quantify the strength of linear relationship between the variables. So see that we are using correlation. Correlation is to quantify the strength of linear relationship. Okay, whereas regression expresses this relationship in the form of an equation. Equation of what? Equation of a. Whereas regression expresses this relationship in the form of an equation. What equation? Linear line equation. Y is equal to beta 0 plus beta 1 x plus e. Okay, so see how they differ graphically. Let's take one example. In students taking mathematics and English test, we can use correlation. We can use correlation to find out whether students who are good in mathematics are also good in English as well or not. Okay, you got the example. In students taking mathematics and English test, we can use correlation to find out whether students who are good at mathematics are good in English. Okay, whereas regression is used to find out whether the marks in English can be predicted given the marks in mathematics. Okay, understood the difference between the two, where we should use the word correlation, where we should use the term regression. So regression is we are doing some kind of a prediction of the marks in English from the given marks in mathematics. Whereas correlation tells you whether people who are good in mathematics, they are also good in English or not. People who are good in mathematics, they are good in English. Okay, this is how these two terms are different. Okay, now let's take one example. And silly example actually, and connect all these terms we have learned so far. So this is again a cooked up example, not a specific example. Okay, so this is a scenario. There are two people, A and B. Okay, they both try to guess the value of variable y. Fine. A has no information except the average value of y, that is y bar. Remember I showed y bar as the average of that? Okay. B knows in advance the value of x and also knows the regression equation that connects x and y. Okay, so the question is who will do better at guessing, A or B? Okay, yeah, the answer is little bit clear, but we need to analyze the situation and find out statistically how does it vary. Their answers, their guess vary. Okay, what will be A's best strategy? A's best strategy is to simply guess that y will be equal to y bar, because A only knows average value of y. Okay, so for any given observation of y, okay, say let's assume ith observation, there will be a certain amount of error, and that error can be captured here. So error I is equal to yi minus y average, because A's best strategy is to say that y is equal to y average. Clear? Okay, so to get a total error of A's plan, Okay, let's say we are going to call this error as SE average, because A is always using the average value to guess. So we will call it SE average. So what is SE average? It is the summation of all the deviations of Y observation from average. That is yi minus y bar. Okay, see that this is also SST, total sum of square. Okay, so what A is doing is A has a Y average value, and here in order to know what mistakes A can do, we are trying to find out the deviation of each point from this average, square it up, total sum of square. Okay, now let's see what B can do. B has advantage because B knows the regression equation itself. Okay, so let's say EI be the error that B will make from the prediction. So what is EI here? EI will be yi minus yi hat, that is actual observation minus the value from the model. Okay, from the model. So if we total this square error, let's call it something called SE line. SE line, which is the summation of all the errors in all the n observations. Okay, and see that this is same as SSE, that is sum of square due to error. So graphically, what we are trying to find out here? Graphically, because B knows the regression equation, we are trying to find out this deviation for B. What is the total deviation B's guess can do, right? So we are squaring all these deviations and summing it up. Okay, now suppose that B's squared error using regression is as same as A, who did not use regression at all. Then I can conclude that regression is worthless, right? Regression is worthless. That is, knowledge of X provides no help in predicting value of Y, right? Everyone agrees? Okay, suppose that SE line is 0. What is SE line? SE line is SSE, sum of a square due to error. Okay, suppose that SE line is 0. In that case, B is able to make perfect prediction because the error term is 0, right? And therefore R square will be 1 minus SE line by SE average, which is equal to 1 minus SSE by SST. So see that R square value is computed from SSE, sum of the square due to error, divided by SST, total sum of square. Okay, what is the intuition behind this? What is the intuition behind this? So see that R square, which is coefficient of determination, is computed from sum of square due to error and total sum of square, SST. And see that R square is 1 if SSE is 0, and R square is 0 if SSE is equal to SST. Okay, R square is 1. What does it mean? R square is 1. Perfect correlation, right? 0 means no correlation, 1 is perfect correlation. So if R square is 1, it means that SSE is 0. Okay, so anything 0 divided by anything will be 0, 1 minus 0 is 1. Okay, therefore R square is 1. If R square is 0, it means that this term is 1. SSE is equal to total sum of square. So therefore this will be 1, so 1 minus 1 will be equal to 0. Okay, so one more conclusion from this discussion what we had. Suppose the observations of X and Y fit along a perfectly horizontal line. Suppose the observations of X and Y fit along a perfectly horizontal line. What will it tell us? We are tempted to say that there is a relationship between X and Y. Why? Because you find a line that can fit all the points. If you can find a line that can fit all the points. Okay. However, notice that for this line, slope is 0. For this line, slope is 0. So changing the value of X will not change the value of y. Okay, what I am talking about is this scenario. Suppose the observations of x and y fall on a perfectly horizontal line. This is a perfectly horizontal line. Okay, now if you keep changing the value of x, y remains same. If y is 5 here, it will continue to remain 5. So it means that slope of this line is 0, so we don't need x to predict y because y is constant here. So r square value will be undefined because it will require division by 0. Okay, this part is clear. Okay, now let's move on to correlation coefficient, which is actually derived from coefficient of determination. Correlation coefficient is also known as product moment correlation coefficient or Pearson coefficient, Pearson correlation coefficient. This is another measure, another quantity that will tell you the strength of a relation, and it is directly related to r square. Okay, so r square is the square of correlation coefficient. R square, which we have learned just now, is the square of correlation coefficient, square of this term. Okay, sign is same as the slope of line, and values of correlation ranges from, because r square is the square of cc, so when you take square root of the cc, values will range from -1 to +1. Okay, what does 1 mean? 1 means perfect linear relationship with positive slope. Perfect linear relationship with positive slope. -1 means perfect linear relationship with negative slope. 0 means no relationship, and this is also a unitless quantity. It does not have any unit. Okay, so what does correlation coefficient do? Everyone is clear about why the range is from -1 to +1? R square is the square of cc, so r square is equal to, let's say cc is some value, cc. Okay, so actually I should not write like this. R squared is equal to square of cc. Cc is also written as small r. Okay, so when you take the square root of this, the range of cc will be from -1 to +1. Okay, got this point? Okay, so what does correlation coefficient tell us? This will measure the strength of linear relationship between x and y. Okay, and also it is unitless, and it's not, this correlation is not at all affected if you perform any kind of a transformation of x and y. If you perform any kind of a linear transformation of x or y, this particular measure, correlation coefficient, will not be affected at all. Okay, and also correlation coefficient does not distinguish between the dependent and the independent variable. It is unitless. It is not affected by linear transformation of x and y, and also it does not differentiate between x and y. Okay, so we have now seen correlation coefficient, and next we will quickly summarize what we have learned. Okay, so we start with a scatter plot, right? Start with a scatter plot to see whether there is any relationship between x and y, independent and dependent variable. Step number 1. Step number 2, compute the residuals, that is SSE, sum of the square due to error, for any line by using that scatter plot. Third step, finally find equation of the best fit line by minimizing SSE, sum of square due to error. Okay, and how is this minimized? Using ordinary least square, which you are going to tell me after the lunch. What is ordinary least square? Okay, so this actually uses differentiation and gradient descent method, and this will help us to find out the final value, optimal value of beta 0 and beta 1. What is beta 0? Constant. Slope. What is beta 1? Coefficient. Coefficient of x. Remember this equation, y is equal to beta 0 plus beta 1x plus e. So this is slope and this is coefficient. Sorry, I told that earlier. Yeah, fine. Clear? Everyone is clear? Any doubts till this point? No, we are not breaking for lunch. Still there are 10 minutes. 10 minutes? Yeah. So we just had tea. So everyone is clear? Any doubt here? So this is just a normal way of calculation, but we will not use this. This is just for our understanding. Okay. Okay. Now we will go ahead and so what do we try to minimize? This error term E. Okay, and what is beta 0? Intercept. What is beta 1? Slope. This we are going to determine from the equation, and values of x will be given, for which we will try to predict y once beta 0 and beta 1 are known. Okay, so r is equal to -1 means perfect negative correlation. R is equal to -1 means perfect negative correlation. Okay, R is equal to 1 means perfect positive correlation. So both are perfect correlation. One is negative, one is positive. Okay, R is equal to 0 means no correlation. R is equal to -0.84 means strong negative correlation. It's strong correlation but negative. And R is equal to 0.15 means weak positive correlation. So when you infer these values in your paper, research paper, please interpret in this fashion. Perfect negative correlation, perfect positive correlation. There is no threshold saying that if it is more than 0.5, call it perfect, less than 0.5, non. It's not. There is no definition, but we judge it according to our application. In some scenario, we will never get a correlation of 1. So maybe a correlation of 0.8 is the maximum we can expect. So in that case, we can say that we have got a strong positive correlation. Okay. Correlation does not prove that one of the variables has caused the other. What does it mean? Umbrella rain. Does umbrella cause rain? But umbrella rain are correlated. Right? We can have many such examples. If we study 20 hours or 15 hours in a day, does it mean that we will always get 90%? Depends on like how much time we actually study and how much time we look into mobile phone, right? So one can cause the other, but we have to see whether there is a theoretical basis. Some people can read only 2 hours. General idea is that you study more, you get more marks. But practically it may not be true, because depends on how much we are concentrated while doing the study, right? So see that both are correlated. Higher number of hours you study, more marks you get, but it doesn't mean that one causes the other. Okay. Graphically, R is equal to -1 should look like that on the top left. This one. R is equal to +1 should look like this. This is strong negative correlation. This is strong positive correlation. Okay, so along with R, you have to visualize how will the graph look like, plot look like. So both are strong correlation, but one is negative, one is positive. This is R is equal to minus 0.06. Why there is a difference between these two? Why there is a difference between these two? Both are negative. One is minus 1, one is minus 0.6. How, in what way they are different? Look at the scatter of the points here. They are more scattered. Here all the points fall in an exactly straight line. So correlation is strong, 1, but negative slope. Okay, see this R is equal to 0. Did you know when is R 0? When I said that by changing the value of x, y will not change. So we don't need the value of x to determine y, because y is already known. Does it hold here in these two cases? In these two cases, by changing the value of x, y will continue to remain same. So we don't need the value of x to predict y. Okay, see that this is a case of strong positive correlation. This is a case of weak positive correlation. Okay, again this is strong relationship here, this is weak relationship. Why weak? Because data don't fall on a straight line, therefore weak. This is no relationship. So now I hope from the data, by looking at the plot, you can conclude what type of relationship can occur. Okay, let's look at one example of what is positive correlation, what is negative correlation. What is positive correlation, what is negative correlation. So if the values of two variables, deviate in same direction, that is, if an increase or decrease in the value of one variable results in an increase or decrease in the value of other variable, it is said to be positive. That means you study more, you get more marks. More study, more marks. Both are positively correlated. Right? Height and weights. So people say that if people are very tall, they should have good weights also, but may not always be true. Household income and expenditure. People believe that more you earn, more you spend, but there are exceptions who will save more money than spending, right? But amount of rainfall and yield of crops. We need rain to have good yield, but it doesn't mean that if flood is there, we'll have good yield. Then all the crops are gone. But see that these two terms are positively correlated. Okay. See the example of negative correlation. So correlation between two variables are negative or inverse if the variables deviate in opposite direction. So more you enjoy with your smartphone, the lesser marks you get. Right? So the variables deviate in opposite direction. More enjoyment, lesser marks. One will go up, one will go down. Okay? Or vice versa. For example, volume and pressure of gas. If you increase pressure, what will happen to volume? Current and resistance, but assuming that voltage remains constant. Okay? Price and demands of good. If there is a high demand of goods in the market, prices will go up. So how is this particular point valid here? Negative correlation. I think this should be supply, or it should not be supply. Negative correlation. Everyone is clear for the cases of positive correlation, negative correlation? Okay. So who will summarize what all we have covered? Nobody is summarizing. we covered different types of correlation: positive, negative, strong positive, strong negative, weak positive, weak negative, no correlation cases, right? And we also saw what causes positive correlation, what causes negative correlation. Okay, so do we break for lunch? Okay, we'll break for lunch, then we'll meet again. So question paper is ready. independent variables are added unless they actually improve the model. Okay, so what does it mean? It means that if you think that if you have 100 attributes, 100 parameters, and if you use all 100 parameters, your model will become close to perfect or almost perfect. This may not be true. Okay, so what the message is that even with lesser number of attributes, lesser number of parameters, independent variables, you can still achieve a high accuracy model or a very good model. So let's say if you have 3 variables, okay, let's take an example. So example is as follows. This will also lead to the discussion for the next topic. So assume that we are looking to purchase a flat in this city, okay, and the purchase, let's say it is some kind of a cost, so we can say that it has an associated price of the flat, okay, and price might be function of many independent variables. So price is a dependent variable. Price will depend on many independent variables. For example, how big is your flat? What is the area of the flat you are trying to look at? So if the area is big, definitely price will be bigger. Price will be higher. Sorry, okay. Then along with price, you might also consider how far it is from the nearest bus stand or nearest metro station, right? So distance from the bus stand or distance from the metro station. So I can have 2 more variables: size of the flat, distance from the metro station, distance from the nearest bus stand. Okay. Then what else you want? You might require parking in your apartment itself. You don't want to park your vehicle on the road, so parking. So if you want parking, additional 1 parameter. If you need parking, prices will go up. Okay. Then what else we can add? Suppose if you want your flat to be on a higher floor, okay, so higher the floor, more is the cost, because you get a better visibility, fresh air and so on. So higher floors means more cost. Okay, so let's say these are all independent variables that keeps on adding to your price, right? But see that distance from the metro and distance from the nearest bus stand might look very similar. If you can walk to the bus stand, maybe you can walk a little bit to the metro. No need to look for a separate flat that is closer to metro station also, right? So we might think that if we keep on adding more and more variables like this, we may be actually able to develop a model that can give us a realistic price, but it is not true. Okay, it is not true. And how do we come to know that? See that if you add more and more number of variables, R square, that is coefficient of determination, can increase, but adjusted R square will decrease. Okay, but adjusted R square will decrease, indicating that please don't add any more variables. We have your addition of new variables is not at all improving the current model. So whatever you have added just now, remove it. Okay, so in general, R square, if it is close to adjusted R square, your model is good enough. Okay, now if you add a new variable, if this improves and this also improves, then it's fine. But only this improves and this does not improve, it means that the addition of new variable is not significant enough. Okay, so adjusted R square is given by this particular expression, 1 minus R square into n minus 1 divided by n minus k minus 1, okay, where k is the number of independent variable and n is the number of data points. Okay, so also see the last point, that ordinary R squared, which is coefficient of determination, which we have learned earlier, will increase by adding new independent variables. So if I keep on adding new variables, now for example, how close the flat is to the nearest market, supermarket, okay, how close it is to the nearest vegetable market, I can keep on adding new variables. So more closer means more price and so on. But it may be true that all these unwanted, all these variables may not be required, may not be important, may not be significant. Hence R square will increase when you add these variables, but adjusted R square may increase or may not increase at all. Okay, so if it does not increase, we assume that these new additions of variables are not important, just leave them. Okay. Okay, now this brings in to the next related topic on moving on from linear to linear regression to multivariate linear regression, okay, where we have more than one variable. So let us look at this original equation of the line y is equal to beta 0 plus beta 1 x plus e, okay, where e is my error term. Now see that if the variable independent variable x is the only variable that affects y, then we don't need to have the term e, error, because it means that x will be completely able to explain variations in y, right? I will repeat, if x is the only variable that affects y, then it means that we can completely explain variation in y by x, and we don't need error term, because we assume that no error will occur, because I can completely explain y by x, okay. So in that case we do not need to worry about any other factor that might be also impacting y, okay, but we have not at all observed them in the data, okay. But suppose in case there is some error term, okay, we can easily model that error term by the variable e. And what is e here? E here is the error term, okay, which turns out to be a random variable having normal distribution with mean 0 variance sigma square, okay, mean 0 variance sigma square. So look at this expression, y is equal to beta 0 plus beta 1x plus e, where e is a normal has a normal distribution with mean 0 and variance sigma square. If the regression what you have done is very good, if the regression model that you have developed is very good, then see that this variance will be very small, error term variance will be very small, because the model is very good. So we expect a small error term, small variance, not much, okay. But suppose if error term is large, okay, then it also means that there are other factors which we have not at all accounted in the model, and therefore apart from this e is too large, and it also means that if error is too large, it might happen that there is some other independent variable, maybe x2 or x3, which we have not at all considered here. Suppose what I am saying right now is, suppose that if x is able to explain y completely, okay, then this error term will be minimum, right? Error term will be minimum. Suppose vice versa, error term is very big, and x is not able to explain y completely, therefore error term is very big, then it also means that why is the error term so big? Why is the error so high? Why is the residual error so high? So it can give us a clue that there can be other factors which we have not at all accounted in this model. Okay, now we are going to capture these factors in this model by another set of independent variables. Okay, that is called multiple linear regression. Okay, so we now, instead of x1, we have another set of independent variables, x2, x3, x4, xk. Okay, so see that y is not dependent on not only, so if y is the price of a house, it is dependent on not only area of the house, but also distance from the nearest bus stand, distance from city center, distance from metro station, and all these are your independent variables, x1 to x3. So here, what is the idea? Idea is that we want to establish a relationship between one dependent variable and several independent variables, 1, 2, 3, 4 and so on. We want to establish a relationship between one dependent variable and several independent variable or several exploratory variable. Okay, so see that this is how we formulate the problem statement, and as the example that I cited is the same. Price of a house Y may depend on area, distance from city center, number of floors, parking space, if hot water facility is available that can be added, and so on. I can keep on adding new features. So all these new features are captured here in the form of x1, x2, x3, also known as independent variables. Okay, so this will be your new multiple linear regression model. Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 and so on. Recall the graph that I had shown earlier between x and y, where x was my marketing budget and y was my sales. Assuming that more money you spend in the budget marketing, more sales will happen, right? Now see that that particular graph has that line what we used to connect the dots has now converted to a plane. Why it has converted to a plane? Because now instead of 2 axes you have 3 axes, one here, one here. So now your points are distributed in such a way that you can fit a plane. It's multi-dimensional. x1, x2, x3, these are new dimensions apart from y. So we had y and x, now we have another variable x2. I can also have the third independent variable, maybe here x3 and then maybe here x4, although it's not possible to completely visualize. But see that now I can use a plane to establish a linear relationship between multiple variables. Okay. All right. Now, when two or more independent variables are highly correlated, how do we know that they are correlated? By correlation matrix. We can make out if they are correlated. Okay, if two or more independent variables are highly correlated, this situation is called multicollinearity. In this case, you will be unable to distinguish, to identify the effect of one on with the effect of on other. Okay, you will be unable to identify the effect of one independent variable with the other. If more than one independent variables they are correlated, you get a condition or situation called multicollinearity. Okay, when the errors of successive observations of time series data, when the errors E term of time series data are correlated, it is called serial correlation. In multiple linear regression, we have now learned two new terms, multicollinearity and serial correlation. What is serial correlation? When the error terms of successive observation, for example, it's a time series data T1 plus T1, T2, T3, where T2 is more than T1, T3 is more than T2 and so on, then these errors, if they are correlated, the situation is called serial correlation. So what is the problem with multicollinearity? Multicollinearity makes it difficult to find out the effect of individual predictors. It means it will be then difficult to find out how is the distance from metro station affecting price of a house, how is the distance from bus stand affecting price of a house, because they might be correlated, causing a case of multicollinearity. Okay, so now how to find out that? So see that we use something called VIF, variance inflation factor, and a variable that has high VIF, means that this particular variable can be largely explained by other variables. Suppose if distance from the metro station has high VIF, variance inflation factor, it means that the information that is present in this distance from the metro station can also be explained by some other variable present in the data. For example, distance from nearest bus stand. So metro station can now be removed because it's a variable which is not at all adding to the model, and it is producing a case called multicollinearity. Okay, multicollinearity. So we have to check, and if it is a high VIF along with the p-value, then it means that some other variable can also explain the same information, hence we can remove them. Okay, I hope you know already what is p-value. So p-value is a level of marginal significance. P-value is the level of marginal significance within a statistical test, and what it does, it provides the smallest level of significance, significance at which the null hypothesis can be rejected. Okay, let us now summarize what are the steps that one should follow while implementing multiple linear regression. Okay, so first of all, start with data cleaning, perform data cleaning. Okay, then convert your categorical variable to numeric variable. So categorical variables can be, for example, yes, no, true, false, and so on. So convert them to some kind of a numeric representation, okay, that you can easily use in regression. In our software, there is a function called model.matrix, okay, that can help you to perform this conversion. Then after this, you can also create some derived metrics. For example, let's say you have a variable number of bedrooms that decides the price of a house. Okay, 2 bedroom, 3 bedroom, 4 bedroom, and you have also something called area of the house. Okay, so area of the house divided by number of bedroom will create another variable. Area of the house divided by number of bedrooms will create another variable. So instead of having area of individual bedrooms, now you can represent one single variable which is a derived variable by dividing area of the house by the number of bedrooms. This will give you an average area per bedroom. Okay, and this can be a derived variable, and you can now remove area of individual bedrooms from the data. Okay, next step. So next step is that as a consequence of this, since not all the variables will be significant, okay, so you can afford to remove some of the insignificant variables that you are sure will not add to the model, and because you have used them already to create a derived matrix. Okay, next, try to see if multicollinearity exists. Use the VIF function, variance regression factor function. If it exists, then you can afford to remove those variables. In our software, there is a package called CAR, C-A-R. Okay, and once you have called upon the loaded the once you have loaded the CAR library, once you load the CAR library, then use the VIF function along with the model name for which you want to compute the VIF for every independent variable. Okay, this will give you the VIF for all independent variables. One which has high VIF can be removed easily. Okay, finally, we know that adjusted R square is better than R square to find out how good your model fits the current data. Okay, so higher the VIF, higher is the multicollinearity, you can afford to remove those independent variables. So idea is that world is simple, let us end up getting a simple model that can also serve the same purpose. There is a very popular phrase in computer science that people often use called Occam's razor. So it says that world is inherently simple. So if a simple model can give you the required output, do not go for complicated models. Unless those complicated models can capture something, some information which your simple models cannot. Do not prefer complicated models. Okay. Now this is the close to the, we are close to the end of this session. Okay, and the second last slide or third last slide is essentially how do we select the variables. So if you have x1, x2, x3, x4 and so on, there are three approaches to get started for considering each variable in the model. The first step is called backward selection. What it means is that select all the variables. If you have 5 variables, x1, x2, x3, x4, x5, select all the variables, okay, and in each iteration keep removing the last one. Then check the R square value and adjusted R square value. If they improve upon the removal of that variable, remove it. Okay. Second way of variable selection is called forward. So in forward selection method, what we do is start with the first independent variable. Y is equal to beta 0 plus beta 1 x plus e. Okay. Once you get the adjusted R square and R square value, add x2. That means y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. Get R square, adjusted R square value. In the third iteration, then add third variable x3 and so on. Okay. The third way of variable selection is called stepwise selection. What we do here is that suppose we have a large number of independent variables, so we actually combine the backward and forward selection method which we have just seen. Okay, so what we do, start with all the variables, drop the one which is least significant in the model. Okay, sometimes you might have to reconsider previously dropped variable for reinsertion into the model depending upon if R square value or adjusted R square value is decreasing. Okay, and the variable that you want to reinsert should have lower p-value than the variable being dropped. So p-value is something that also helps us to decide whether do you want to keep a certain variable or remove a certain variable. Finally, use AIC, that is a key information criteria, to reduce the number of variables in the model. Okay, in the model, observing certain observations followed by VIF and p-value. So in our software there is a package called a library called package called MASS, MASS. Okay, so once you run this command, what it will do is in front of each variable it will put a plus sign. So for whichever variable it has put a plus sign, you can easily close your eyes and remove them. They are not at all significant. Okay, so how do we detect multicollinearity? Multicollinearity can be removed by the variance inflation factor VIF. Okay, so independent variables that have high VIF and low p-value, low significance, sorry, high p-value and low significance, in the sense that they have higher p-value. Higher p-values means those variables have lower significance. So if a variable has high VIF, okay, and low significance means higher p-value, then remove it. Okay, I think, yeah, this is the slide that explains this. So multicollinearity can be checked using VIF and remove variables that have high VIF and low significance. That means p-value is more than 0.05. Sometimes the variables with a high VIF, sometimes, I am saying sometimes, the variables with high VIF may be statistically significant. That means their p-value will be very low. See, p-value is less than or equal to 0.01. Sometimes the variable might have, or variable may have high VIF and may also be statistically significant. So in R, it will put a star symbol against those variables which are statistically significant, which have p-value very small. Okay, if this is the case, If this is the case, see this, why I am putting the second bullet. Look at the first bullet, then you will come to know that second bullet is the opposite condition. First bullet says high VIF and p value more than 0.05, remove it. Second case says high VIF but p value is low. P value is not high, p value is low. It means that that variable is statistically significant. If this is the case, then you will have to first check for other insignificant variables where p value is higher before you remove this particular variable. Okay, so continue removing the variables until you see that all the remaining variables are significant or they have p value very small and also low VIF. Okay, finally you are going to arrive at a model where all the variables are significant and there is no multicollinearity. Okay, then you can check the model for accuracy. So how do you use p value? So you formulate a hypothesis that null hypothesis that variable not significant, okay. So if p value is higher, greater than 0.05, we fail to reject this. Means variable is insignificant. But if p value is low, then we have to reject this and accept that variable is significant, so we have to keep it. So if p value is smaller, then it means that variable is significant. Please retain it in the model. Okay, so why we are discussing all this here? Because now we have more than one independent variable. Earlier that was never a problem because we had one dependent, one independent, so everything was simple. Now because we have more and more independent variables, we may or may not be able to retain all those variables in the final model, right? But how to decide which one to retain, which one to throw off? Using this kind of a statistical test, using VIF, using p-value. Okay, the last slide is something for you to think about. So let's say once you have developed the model, everything done, so then question is at least one of the predictors, x1, x2 and so on, useful in predicting the response? Just think over your own problem statement. When you have, this is a general statement, but in your own context, for your own application, for your problem, look at each of the independent variable and find out if one of them is useful in predicting the response. Does all the predictors help to explain why? Does all the predictors help to explain why, or is only a subset of the predictors useful? Okay, so in what context? So think of price of that flat. There may be hundreds of factors I can keep counting in: generator facility, hot water facility, filter facility, but may not all be useful. Few of them will be very important. Okay, how well does the data, how well does the model fit the data? How well does the model fit the data? Okay, and given a set of predictor values, what response value should we predict and how accurate is our prediction? Given a set of predictor value, what is predictor? Your x values, independent variables. What response value should we predict and how accurate is our prediction? How accurate is your regression model? Okay, more details on these 4 points are discussed in this particular book. Book name is An Introduction to Statistical Learning with Applications in R, in page number 75. This is a free book. I mean, you can just type in Google and download it. PDF is available. Okay, so this was the last slide. Now we have 1.5 hours. Okay, now we can do two of the following things. Either I can first give you a demo of what we have learned right now, or I can cover logistic regression, then give a demo and end the class. But I will not be able to cover the demo of logistic regression because time will not permit. If we have to finish by 4:15 or so for this one, right? Demo for this one. Then if time permits, I can cover logistic regression. Okay. Yeah. I will give you the data and the code, and you can also run it yourself. I have put the comments. Okay. So first let us see one example of a linear regression. Okay, then we will see the same extend the same example to multiple linear regression. Okay, so is the Excel sheet visible to everyone? Okay, so see that I have one independent variable, one dependent variable, and the independent variable is price. Okay, and the dependent variable is area. So depending upon the area, price should change. Okay, so sorry, price is your dependent variable, area is your independent variable. Okay, so your price is y, which will depend on the independent variable area. Simple problem. Okay, so there are almost roughly 200 data points. Okay, and don't worry too much about the values, because it's a kind of a dummy data. So the price and area may not match exactly in that fashion. It's not a real time data. Okay, then in another example for multiple linear regression, see that price now is a function of area of the house, distance of the house from city center, and how many floors or on which floor the flat is situated. Okay, so I assume that y will be a function of these three parameters. Okay, we can add more number of variables. Okay, but let us restrict to one dependent and three independent variables. Okay. Okay, so I will now open the code and So I will go through each line of the code. Is it visible or brightness is slightly reduced? No. I will share the data and the sheet both. How do I share that? Sorry? Huh? So what do you want right now? This Excel sheet. But more important is the code file. Okay. Sorry. One more thing. My laptop is not connected to internet here because I do not have access. I can give you after the class. It will take another 10 minutes to distribute. No, I will go through each line. And as I told, what I have done is, see, I have written a comment before each line. I have written a comment before each line. You have pen drive? Okay, give it. Okay, shall we go through the lines of the code? Okay, so I have already shown you the Excel sheet for linear regression with one dependent variable and one independent variable. Okay, so this is a demonstration of the simple linear regression program. Okay, so first thing what we do is import the data in R. Okay, so what I have done is kept my data in D drive. So therefore you see that the path to D drive is specified here, D:\/ and then file name. Okay, remember to give this detail. If you put it in other directory, other folders, remember to change this particular detail here. Okay, now we are going to check the structure of the sales data. Okay, so this is the data. See in the bottom left box. So we have two variables, area and price, and there are 200 observations, 200 data points for each of the two variables. Okay. Now what way they are related? Okay. So this is the particular graph that you can see on the bottom right, sales area versus price. Okay. And the data are slightly clustered at the origin, but as soon after as the values increase, they become a little bit distributed. Okay. Now next thing what we are going to do is use a seed function. Okay. And what we want is, currently definitely we are not going to use the entire data to create the regression model. We would like to keep some part of the data for creating the model and some part of the data to test the model. Okay, this is the normal way people approach this kind of a problem in machine learning. Okay, so the general norm is that use 70% of the data for training and remaining 30% of the data to test how good is your model. So 70% of the data for building the model and 30% of the data for testing the model. Okay, right. So we use the set.seed function, and the idea of using the set.seed function is to see that we produce the same result each time while we sample the data set. Okay, so we set seed as 100. Okay, and now out of all the data records or observations what we have, we keep 70% of the data in a variable called train indices, in a variable called train indices. Okay, so what we are doing now is creating an object called train.cells, and we are going to store 70% of the data which okay. So so now we are going to create an object called train.cells, and the idea is that we are going to store 70% of this housing data, okay, by passing the indices that we have just built for the housing data set. So let's call this variable train.cells and keep those 70% data in that particular variable. Next, what we do is keep remaining 30% of the data in the another variable called test. Okay, now we are going to use the train.cells variable for building the model, regression model, and test variable to test the model that we are going to build, or how to see how accurate is the model. So we now try to develop a model using a function called LM. LM means linear model. It's an inbuilt function in R, and what we do is there are three input parameters. The first one is the dependent variable, that is your price, and the second one is independent variable, that is your area. Okay, and this symbol means that we are going to regress dependent variable against independent variable. Okay, and the third input to this is the data, that is the training data frame that we have just created using the variable train.cells. Okay, so now we make this model, build this model using the LM command, and see that we are going to regress price and area using the train.cells data set. Okay, now the model is ready, the linear regression model is ready. Okay, and it is stored in the variable model. Okay, so now it will be good to see what are the results in the model that we have got. Okay, so for that we use a command called summary of the variable model in which the model results are stored. Okay, So see that the summary is now displayed here at the bottom. Okay, so in the beginning the model function itself is stated, that is the formula to regress price and area with the data train.cells, and then you see the details about the error term, the residuals. Okay, so details about the error, for example minimum, first quartile, medium, max, etc. are given. Then below that you can see the coefficients. Okay, and in that you I think you can make out intercept and the slope is given. So along with that you can see the estimated standard error, estimated values of the coefficient standard error here, and t value here, and p value here. Okay, so what is in the equation that we have learned, y is equal to beta 0 plus beta 1 x. What is beta 0 here? So beta 0 is 7.22. Okay, and what is beta 1 here? Beta 1 is 0.04. Okay, this is the standard error. Standard error, it means that the the estimates can have a standard error of plus minus these values. Okay, t value is actually a ratio of the first two columns, estimate and standard error. Okay, and this probability p value tells us the significance of each variable. So see that there are 3 stars which indicate that both the variables are important. Okay, or area is important. Okay, and then along with that you see that there is one you see that a minimum residual error is given, and along with that multiple r squared and adjusted r square are given. So we have covered both the r squared value. Okay, both r square value, and see that multiple r square and adjusted r square are almost same, almost similar, 0.62 value, right? 0.62. So it means that the model, the variables that you have used in the model are all significant, and there is nothing we can remove. Okay. Okay. Next is we have built the model. Now what we will do is we will apply this model and test it on the test data. So for the test data, your x are given and we need to predict y. X are given, we need to predict y. So for that 30% of the data has already been kept in another variable called test. Okay, so we execute this command, and now output of this test is now stored in another variable called predict_1. So we are using a predict command. Predict is a command that will allow us to use this model that we have currently built and apply this on the test data. Okay, so now test in predict_1 the outputs are stored. Now what we will do is we want to now compare what is our actual observation and what is the predicted output from this model. Okay, so to do that, what we will do is on one side we will keep the original observation that we kept separately. Okay, and on the other side we will use all the values that are now stored in predict_1 from the model, and we are going to do one-to-one comparison. Okay, so what we are doing in summary is that we have 30% of the data, labeled data as test data. Okay, these are input to the model and the model predicted something. So we have actual observation for the 30% of the test data and the model predicted outputs. We are going to compare them to see how good is our regression model. Okay, so what we will do is put all the values, assign all the values of this new prediction into one variable test, and keep it aside with the original observation, so that we can compare them one to one, how far they are matching. Okay, so it is now done in the same file, in the same variable. We have actual observation, we have predicted observation. Next, let's try to find out how well these two, actual observation and predicted values, how well they are, actual observation and predicted values correlated. Okay, so to do that, there is a function called COR, which computes the correlation. Okay, and this is now computed. So see that the correlation between actual value and the ones predicted from the model is 0.76, which is, we can at least not very strong, but we can say strong positive correlation. Means the one from actual observation and one from the predicted from the model are close by. Okay, and also we can say that 76% of the variation is being variation in Y is being explained by X. Okay, now let's compute R squared value. Okay, and let's see R square value. So R square value is 0.59. So earlier one was correlation, and this is what? R square value, coefficient of determination. Okay, so now we have been able to build a simple linear regression model with one independent variable. Okay, fine. Now let's proceed and look at another example. Look at another example of this particular case when we have three independent variables. Okay, and how do we use these three independent variables to build a multiple linear regression model? Okay, so let me open a new file. This code I have also shared with him. Hope all of you have got it. Okay. So this is the code for multiple linear regression. Okay. Again, I have stored it in a different directory. So please change your directory in your own laptop. Okay. So first thing is, let's try to read the data. Okay, so we have read the data in a variable called sales1. Okay, and now let's see the data. So see that we have three independent variables: area, distance, floor. Okay, see the Excel sheet. Right, same data now we have read in the R platform: area, distance, floor, and price. Okay, now next what do we do is we are going to check the structure of the variable. So this is the structure of the variable. Okay, there are 200 observations of four variables as listed here. Okay, now what we will do is first build a linear model using the same lm command, that is linear model, and we will store the output of this linear model into an object called model_1. Okay, so similarly we have model1 where we are model_1 where we are going to store the output of the lm command, where price is regressed with the other remaining independent variables, and the data for this is sales1, which we have just read. Okay. Okay, so model is now ready, and now let's look at the summary of the model. Okay, so this is the summary of the model, and see that in the first place the lm command itself is stated, where price is regressed against all the other independent variables from the sales data. Then this is the details about the residuals, minimax, etc. And then again we have intercept, that is with beta 0, and the coefficients. What are these three values? This one, this one, and this one. What are these three values? What are these three values? Huh? So in that expression, what are these? Beta 1, beta 2, beta 3, right? Beta 1, beta 2, beta 3. This is the standard error, and t value is the ratio of the first two columns. And also to notice here that these two variables, area and distance, are statistically significant. They have very small p-value, whereas floor is not statistically significant for this model with this data. Okay. So what we are going to do now is, along with that, look at the multiple R square. If 0.89 adjusted R square 0.89, both are almost very close. So all the variables are good enough at this point, and we are getting a multiple R square value and adjusted R square value almost same. Okay. Then see that there were 200 observations. So out of that, minus 4 variables, you have 196 degree of freedom. Okay. And now let's move on. Where is summary model 1? Okay. Okay. So now we also observe that floor may not be a significant variable here. The floor independent variable may not be a significant independent variable here. So let's do one thing. Let's try to regress price versus floor. Let's try to regress price and floor and see how good model we can develop. Okay. So let's create another model. Okay, and let's call it new model. So in the new model, I have regressed for price and floor. Okay, and now let's look at the summary of new model. Okay, summary of new model. So this is the summary of new model, and this is the summary of old model. Okay, so let's look at the summary of new model. In the new model, we have tried to regress price and floor. Okay, so see that floor turns out to be not a very significant variable, and also look at multiple R square value. It is so low. Okay, look at adjusted R square value. It is even lower than that. Okay, so now we are almost sure that floor is not a very important variable to be considered in this model. Okay. Okay, now what we do is that let's build a correlation table, because we know that multicollinearity can be checked using what? VIF and correlation. So let's build a correlation table and see how it looks. See, so diagonal elements are 1, okay, and see that for the floor and the correlation between floor and distance is 0.35, so, and area and floor is 0.06. So what does it mean? Floor and distance. Floor and distance. Floor and area have a very small correlation, and floor and distance are somewhat correlated. Right? Floor and distance are somewhat correlated. So it means that the information that distance is providing in the model can also be captured using the floor variable. Okay. So now let's do one thing. Let's try to remove this floor variable and then check R square and adjusted R square and see whether it comes down or not. Okay, so we are going to create one more model called model 2. Okay, where I have removed the floor variable. Okay, and what we do is regress price and area and uh, and distance. Okay, so let's look at the summary. Okay, so see that after removing the floor variable, okay, the other two variables are significant because they have very small p-value, and look at the r square and adjusted r square. So almost with no information loss, we have been able to retain same model properties as compared from r square and adjusted r square. Okay, and see that this model almost gives the same accuracy that we had obtained by using the three variables. So it means that we can easily afford to remove the floor variable, and then what will be your final regression equation from this particular summary? Price is equal to 2.92 plus 0.04 into area plus 0.18 into distance plus E, standard error. Okay, so we have been able to develop a very simple model with only two variables that can capture high variation in price with respect to area and distance. Okay, so this is a simple demonstration of the multiple linear regression. Okay, please try the same thing from the files I have given. Since the codes are written, in the comments are written, you can read and make out and execute them. Okay, now I am going to minimize this, and just give me 1 minute. Let me open the file. And let me now try to cover some portion of logistic regression. Okay, so what is shall we take a just small 5 minutes break? Okay, sure. please call everyone. Let's start now. Okay, shall we start now? We need to finish in half an hour. So your certificates are waiting. Okay. So let's get started. So this part of the talk, another half an hour, 40 minutes, okay, will be focused on another set of technique called logistic regression. Okay, and don't look at go by the name. Logistic regression has altogether different purpose. Okay, and it is nowhere closely related to prediction. So what is logistic regression? It is a supervised classification model that is used widely in different domains: finance, healthcare, banking, and so on. Okay, so let's say that a finance company wants to know if a particular customer is going to default or not. Okay, and let's say which patient is possibly diabetic based on several parameters, medical parameters of the patient, or whether an email is spam or not. And we can extend this problem to multiple logistic regression. Okay, we can extend this problem to multiple classes also, or a multi-class problem, depending upon whether you have more than one class in that particular scheme. Okay, so in this part of the talk, in next half an hour, we are going to cover binary classification, sigmoid function, likelihood function, and how to build a logistic regression model in R. While we may not have a demo here, but I can just quickly tell you in one slide, and then you can later on do it by looking at the code itself. I will give you the code. And odds and log odds. Okay, so revisiting the same slide that we had seen earlier. Okay, and to link that now we have moved away from prediction to classification. Okay, from prediction to classification. So in classification, which is slightly different from prediction, what we do is we try to predict categorical class labels. So these labels can be discrete, or these labels can be nominal. Example, 1, 2, 3, 4, 5, A, B, C, D, E, blue, green, red, and so on. Okay, so to do that, what we first, as a preliminary step, what we do first is we try to build a model, construct a model from the available training data. Remember, in the previous example, we took 70% of the data for building the model and kept remaining 30% for testing the model, right? So here again, in a similar way, we keep 70% of the data for training the model and remaining 30% for testing the model. Some people also used 80-20, 80 for training, 20 for testing. Okay, and now currently see that what we are discussing right now is a classification model that will predict categorical class labels. Okay, so let's now try to compare regression and linear regression or holistic regression, and make sense of why they are different and in what sense they are different, in what ways they are different. So recall that in linear regression, regression output was a numeric variable, okay, whereas in logistic regression the output is a categorical variable. So this is the first difference. Linear regression gives you a numeric variable, and logistic regression gives you a categorical variable. In terms of functionality, linear regression actually was used to explain the relationship, okay, to explain the relationship between independent and dependent variable, and we had used a straight line to do that, okay. Logistic regression on the other hand is used to predict the value of the dependent variable in future. Either it can be a binary case or it can be a multi-class problem, okay. So in this way the two techniques are different and therefore they have different application, different usage altogether, okay. So now we are going to take up one example and see in what way logistic regression is used, okay. So let's say that we have to predict whether a patient is diabetic or not. Okay, so we have to predict whether a patient is diabetic or not. And what data we have? We have data that has attributes like blood sugar level, cholesterol level, cardiac, and so on. Okay, so now for simplicity we are going to consider only one variable, that is blood sugar level, to predict whether a patient is diabetic or not. Okay, so we have a simple data, as you can see here, diabetes data with blood sugar level in the first column and corresponding label whether the patient is diabetic or not in the second column. Okay, now what is the first thing we should do? This problem is given to you, okay, and we know that it's a classification problem. What does the classifier do? Classifier predicts categorical value, right? Categorical value. So your output is a categorical variable. So in order to do a classification on this data, what is the first thing we should do? Anybody guess? You can guess. What is the first thing we should do? Huh? Categories are yes and no. Person is diabetic, non-diabetic, diabetic, or diabetic, non-diabetic. Two classes. What range? No. What I'm currently asking is that this is the data given to you. Okay. Now you want to build a model. You want to build a classifier where you give blood sugar level as the input. It will tell you whether the patient is diabetic or not. Okay. I want to build a model using this 10 data points. Okay. So this is your sample data. I want to start. Go ahead, build a model. What is the first thing I should do? Huh? Sorry? No, here assume that we are going to build a logistic regression model. Assign? Yes, assign what? Please go ahead, you are approaching to the right answer. Sorry? To? Very good. First, you should convert your no and yes to numeric variable. How will your computer understand whether it's yes or no? It can work in bits and bytes, right? 0 and 1s. So how will it know it's no or yes? So I will represent them by some kind of a numeric representation, no and yes, no as 0, yes as 1. Okay, then next let's plot the data. Let's plot the data. So we have blood sugar level on the x-axis, diabetes on the y-axis. Okay, and this is how your data looks. All the non-diabetic patients are shown in red dots at the bottom. All the diabetic patients are shown as blue dots on the top. Okay, now what shall I do? I want to decide a threshold, as you rightly said, below what is diabetic, below what is non-diabetic. Okay, so I am going to say that I will decide a threshold and draw a straight line there. Okay, see the straight line, which I am going to call it as a decision boundary. Decision boundary. Okay, and also see that this decision boundary is at the value 210. Okay, now as per this decision boundary, there are two data points which are misclassified. What it means is that the patient had high blood sugar level but is non-diabetic, and one patient has low blood sugar level but is diabetic. That can happen, right? Maybe because of the test because of the time at which the test was done, maybe the patient may have high blood sugar level but the patient may be non-diabetic. Sometimes it can happen. So see that while using this as the decision boundary, there are misclassifications. Okay, so what we will do is let's shift the decision boundary from 210 towards 200. Okay, so now one data point is taken care, but we have one more misclassification at the bottom. Okay, so it means that deciding the class boundary based on cutoff is risky. We need to actually model the distribution of this diabetic and non-diabetic data. Simply taking a line may not suffice here. Okay, so one way to actually address this problem is that instead of diabetic, non-diabetic, okay, let's assign a probability of having diabetes to people. Instead of saying that he is diabetic, he is non-diabetic, let's assign a probability. Okay, let's assign a probability to these patients having different blood sugar level. So by doing that, you see that these people will have extremely low probability of having diabetes. These people will have medium probability of having diabetes. These people will have high probability of having diabetes. Agree? Okay. Now what we want is to model this distribution of data having different probabilities. Okay, so one way to draw a curve and model this data distribution is to use a sigmoid curve where probability of having diabetes is given as 1 divided by epsilon minus beta 0 plus beta 1 x. Okay, and see that this particular S-shaped curve, also called sigmoid curve, has the properties that we are looking for. What properties? Extremely low values at the beginning, intermediate values in the middle, and high values in the end. High values in the end. Okay. Now see that there are two coefficients, beta 0 and beta 1, which we need to find out here also in the denominator. Okay, so let's assume that for a particular value of beta 0 as minus 15 and beta 1 is 0.065, this is the sigmoid curve that we get. Okay, this is the sigmoid curve that we get, and also see what is the y-axis level, probability of diabetes, not diabetes, probability of diabetes. So this particular sigmoid curve has now the extreme low values in the start, extremely high values in the end, and intermediate values in the middle. Okay. Now question is, what are the best values of beta 0 and beta 1 for these data points what we have? For these data points that we have. Okay. And another question is, why can't you just fit a straight line, something like this, which we have learned in linear regression? Okay, so see that a straight line is not steep enough. The values rise very uniformly. So this will not be sufficient to model our data of having diabetes. Okay, so now the next point is, how do we find the best fit sigmoid curve for this particular data distribution? Okay, so let's recall back. In regression, what did we do? In regression, we try to minimize total sum of square, right? And on a similar note, what is that we should minimize, maximize here? In linear regression, we try to minimize the residual. Okay. On a similar note, what is the cost function that we can minimize or maximize here? That we minimize or maximize here. Okay. So let's take the discussion forward and see what do we need. What do we need here? So intuitively, we want the points, that is people who do not have diabetes. Okay, that is for those people who do not have diabetes. For those people, we want the probability of having diabetes to be as small as possible. Okay, because the patient is non-diabetic. So we want the probability of having diabetes to be as small as possible. Okay, so look at this curve now. What we want right now is, we want these red ones to be as small as possible, because these people are non-diabetic, first 5 people. So their probability should be as small as possible. Okay, I am going to skip this slide now because I have already explained, and this slide also. But the idea is to see that here we were actually minimizing this term, right? This term. Now look at this particular graph and see that we are trying to minimize these distances here. The red arrows, can you see the red arrows? We want to minimize those probability for people who are non-diabetic. Okay, so now let's go ahead and see that if I want to minimize P1, minimize the probability of having diabetes for patient P1, can I say that I want to maximize 1 minus P1? Is it same thing? Right. So now I want to maximize 1 minus P1. Okay. So now we see that one expression that is going to maximize all their numbers here is maximum of the product of these probabilities, that is 1 into P1 into 1 minus P1 into 1 minus P2 into 1 minus P3 into 1 minus P4 into 1 minus P6 into P5, P7, P8, P9, P10. Okay, this is the cost function. This is called the cost function that we want to maximize. So what we want right now is best fitting combination of beta 0 and beta 1 that will maximize this product, that will maximize this particular product. Okay, this is called a likelihood function. This is called a likelihood function. And the process where you can change, where you can vary beta 0 and beta 1 until you find the best fit sigmoid curve, or until you find the best fit sigmoid curve that can model the probability of having diabetes, is called logistic regression. Okay, so now let's pick up some random value of beta 0 and beta 1. Say beta 0 is minus 10, beta 1 is 0.03. Okay, so sigmoid curve will look like this. Let's now compute the likelihood and see that product of all the probabilities will be equal to 1.75 into 10 to the power minus this, which is very small. Okay, Let's now change the value of beta 1. So beta 0 remains same, beta 1 is 0.06, and let's calculate the likelihood again. So this is the sigmoid curve, and likelihood is now 0.03, which is more than the previous case. Okay, so the best fit sigmoid curve would be the one that will correspond to the maximum likelihood value. The best fit sigmoid curve will be the one that will correspond to the maximum likelihood value. Okay, so in R it is quite simple. Again, use the lm command, read the file, use the lm command, and call the glm command. Sorry, here it is called glm, not lm. glm is generalized linear model. Okay, and then you can see the summary of the model. So it turns out that for a beta 0 value of minus 13.52 and beta 1 value of 0.063, you will be able to exactly get the maximum likelihood value, which corresponds to 0.594, Okay, so this is how you are going to attempt the problem, solve the problem using a sigmoid curve. Okay, now we are going to address something called odds and log odds. Okay, why we need to worry about odds and log odds at this point? Look at this expression. Okay, isn't this expression not very clear? For example, if X, that is your blood sugar level, increases by some constant value, okay, how will it impact the probability? We cannot tell this by looking at the expression. Suppose blood sugar level increases by 10 every day because of some food that we are eating or having, which we are not aware of. Okay, so how is that going to affect the probability of having diabetes? We cannot say by looking at the expression. Okay, so we need some other simple way to interpret this. Okay, because we are not getting an idea of what the trend will exist if X is changed. Okay, so let's say if we increase the blood sugar level by some constant 11.5, how will that affect the probability? Will the probability also increase by regular interval? If not, what will happen? Can we think of a linear form of this equation? Okay, let's see. See that P is equal to 1 plus e to the power minus beta 0 plus beta 1x. Okay, we have seen in the last example. Now you can slightly rearrange the terms and get 1 minus p. Rearrange the terms here and get 1 minus p. Okay, now let's consider this is equation 1, this is equation 2. Okay, here you divide 1 by 2. So p divided by 1 minus p will be equal to e to the power beta 0 plus beta 1x. Okay, and if you take ln on both the sides, it will be ln of p by 1 minus p is equal to beta 0 plus beta 1x, where beta 0 is minus 13.5 and beta 1 is 0.06. Okay, now let's try to interpret what is p divided by 1 minus p. So we know that p means probability of having diabetes. What is 1 minus p? Probability of not having diabetes. So probability of having diabetes and probability of not having diabetes is called odds. Okay, and if you take log of on both sides, it turns out that ln of p by 1 divided by 1 minus p is log of odds. Okay, so if p divided by 1 minus p is 4, it means that probability of having diabetes is 4 times the probability of not having diabetes. And if probability of not having diabetes is 20%, it means that probability of having diabetes is 80%. Okay, let's see one example. If p is 0.5, 1 minus p will be 0.5. So p divided by 1 minus p will be 1. Okay, if odd is 2, p P will be 0.67. It means that given the value of P, I can compute odds, given the value of odds, I can compute P, and I can keep going back and forth between odds and P. So now, instead of probability, we have odds and log odds. Now, instead of probability, we have odds and log odds. Okay, log and log odd. Now, it will be really interesting to see the relationship between odd and probability. Odd and probability. Okay, so if we increase P, what will be the effect on odds? If we increase P, what will be the effect on odds? Look at this equation. If we increase P, what will be the effect on odds? Huh? Increase, decrease? It will increase. See this. If probability is 0, odd is 0. If probability is 0.25, odd is 0.33. If probability is 0.4, odd is 0.67. If probability is 0.5, odd is 1. If probability is 0.6, odd is 1.5. If probability is 0.75, odd is 3. If probability is 1, odd is infinity. Okay, now having got overall picture of what we are currently looking at, let's go back and look at the entire table. I have blood sugar level in the first column, probability in the second column, odds and log odds in the third and fourth column. So let's now plot blood sugar level on the x-axis, and instead of probability, let us plot log odds. See that we are getting a very nice trend. Okay, so if your blood sugar level increases by a regular interval, we are going to definitely interpret that by means of log odds, but not with the help of probability. Okay, so now the following question is, how does change in blood sugar level affect odd? How does change in blood sugar level affect odd? Okay, so we know that P divided by 1 minus P is epsilon beta 0 plus beta 1x, but how does change in x affect log? How many of you here like to have rasgulla or any sweet dish? Suppose you are given one rasgulla every day in the lunch. How is it that? You don't like or you like it? Everyone likes it, right? Okay, see this now. This is your normal lunch. Your blood sugar level is 220 after the lunch. Corresponding odd is 0.74. Next day, you had one rasgulla in your lunch. Okay, and assuming that your blood sugar level went up by 11.5. Okay, so your new blood sugar level is 231.5. Corresponding odd is 1.48. Since you are fond of rasgulla, second day you ate 2. Think that if we have gone for a marriage party for 5 days, lot of eating, no restriction, so had 2 rasgullas. So 11.5 plus 11.5, blood sugar level went up to 243. Corresponding odd is 2.96. Third day, 3 rasgullas after lunch. Blood sugar level went up to 254.5, and your odd is 5.9. But something very hidden information is there. Look at the jump between odds. Jump between odd is a multiple of 2. Okay, so if x changes linearly, if you keep adding one rasgulla every day to your lunch, to your menu, 1 then 2 then 3, it will have a multiplicative effect on odd. It will have a multiplicative effect on odd, but the good news is that we will be able to interpret the results very easily, because in earlier discussion we saw that the relationship between blood sugar level and probability was not intuitive, whereas here the relationship between x and odd or log odd is intuitive. Okay, so now here it will make sense to take all your major decisions, data driven decisions, using this interpretation rather than going with the probability. the same problem can be actually extended, and now you will have multiple independent variables x1, x2, x3, x4 and so on, and the normal way of proceeding is again missing value imputation, outlier treatment, and then standardizing the scales of continuous variable, dummy variable creation for categorical variables, which we did in the beginning, okay, and then go ahead by building a logistic regression model in R using the GLM command. Other steps including using AIC, VIF, p-value to eliminate the insignificant variables continues to remain same. Okay, and your final model will have all the significant variables. Okay, now do you already have knowledge about how do we assess accuracy of models? True positive, true negative, false positive, false negative. You have already knowledge about this? No? Okay. So for a binary classifier where you have only two outcomes, yes, no, diabetic, non-diabetic, true, false kind of thing, you will have 2 by 2 contingency table. Recall we also talked about contingency table in the beginning, right? Also it is called a confusion matrix or error matrix. So on the row you have actual observations, and on the columns you have predicted observations, predicted values from the model. Okay, and we try to compare actual versus predicted and find out how good is your model. Okay, so see that the way we try to assess accuracy in linear regression is different, and in logistic regression is different. Why? Because there, what is the output? In linear regression, what is the output? What kind of output do you get? Continuous variable. What is the kind of output here? Categorical. So I cannot compare A with A, right? I need some way to find. See, there what we were doing, we were using some kind of correlation, coefficient of determination, R square, etc. Right? But here we cannot adopt the same process because we do not have continuous values, but we have categories: blue, green, red, true, false, yes, no. For example, in your Gmail, promotional and official. So we have those kind of labels. Okay. In order to compute accuracy for labels, people go with something called confusion matrix. And what we do here is, for every test case, we compare the true outcome with the estimated outcome from the model and put the results here. So if your actual output is yes, and model also predicts that as yes, it is going to be true positive. If your actual output is yes and model says no, then it is called false negative. If your actual output is no, actual means observed, okay, and model says yes, then it's called a false positive. And if your actual is no, predicted is no, it's called a true negative. So see that true positive and true negative are the correctly classified data points, whereas the non-diagonal elements false positive and false negative are the wrongly classified data points. From this matrix we can derive few very important metrics that are used as indexes for accuracy. One is sensitivity, specificity, false positive rate, false negative rate, and accuracy. Sensitivity is defined as true positive divided by true positive plus false negative. That is true positive divided by true positive plus false negative. This is sensitivity. Okay. Specificity is true negative divided by true negative plus false positive. That this. Okay. Accordingly, we calculate false positive rate, true negative rate, and overall accuracy is defined as the sum of true positive plus true negative divided by all four. That is these two divided by all four. That is called overall accuracy of the of your model. There are some more error measures which I will skip for the time being because these are not directly relevant here. These two are very popular measures of accuracy assessment called hold out method and cross validation. Okay, hold out method and cross validation. So in hold out method what we do is we divide the data into 2/3 and 1/3. 2/3 is used for building the model, 1/3 is used for testing the model. Did we use 70-30 in our linear regression? 70, is it not close to 2/3? 30 is not close to 1/3? You can use 80-20 also. So you compute the accuracy and note down here x1. Again shuffle the data. Again divide into 2/3, 1/3. Again compute accuracy, note it down here. Do this 10 times. Compute the average accuracy. That is the accuracy of your model. Okay, this is called hold out method. The other very popular method is called cross validation. So in cross validation we try to adopt k-fold cross validation where k is equal to 10 is very popular. So what do we do here? We have a data, divide this data into into 10 mutually exclusive parts. Okay. Okay. In the first iteration, use 1 to 9 for training and 10th one for testing. Okay, report it here, x1 accuracy. In the second iteration, use 2 to 10 for training, 1 for testing. Report the accuracy here, x2. In the third iteration, use 3 to 10 and 1 for training and 2 for testing. Report it here, x3. Keep on doing this. So what will happen is that every partition will get a chance to be in part of training as well as testing. Do this 10 times, compute the average, that is your overall average. That you will report in the report or paper or publication wherever. Okay, I will skip ROC curve. Now this is the last slide before I will give you how to interpret the how to put a threshold to your logistic regression output. Okay, so precision, recall and F score are very important measures. What is precision? Precision means exactness. Okay, so it means what percentage of tuples that the classifier labeled as positive are actually positive. Okay, leave it if you do not understand, don't worry. The formula for precision is true positive divided by true positive plus false positive, which you can see that can be derived from the confusion matrix. Recall is same as sensitivity, which means that completeness. Okay, what percentage of tuples did the classifier label as positive? Again, leave it if you do not understand. Okay, both of the score is 1. Okay, now let's take one example to make sense of what I said about precision and recall. Suppose you do a Google search, you type KSTA Academy in Google search or any search engine. Okay, and the search engine returns you 30 pages, out of which only 20 are relevant. Scenario number 1. Okay, at the same time the search engine did not return 40 additional pages. Okay, what is the scenario? You do a search of some keyword, KST Academy, the search engine returns 30 pages, out of which 20 pages are relevant, 10 pages were not that. Okay, and at the same time 20 pages were relevant, and at the same time 40 additional relevant pages the search engine did not return. This is the scenario. Okay, so precision will be 20 out of returned total number of pages returned 30, which is 2 by 3. Recall will be 20 pages out of 20 plus 40 additional pages which did not return, which is 20 by 40, which is 20 by 60, which is 1 by 3. Okay, so in this case precision means how useful the search results are. So how useful it is? 20 pages relevant out of 30 pages. Okay, and recall means how complete the results are. So see that only 20 pages were returned out of 60 pages. 40 pages the search engine did not return. So precision means usefulness, and recall means completeness. Usefulness, completeness, precision, recall. Okay, using precision recall we also compute F score, which is again widely used in many research paper. They will say F score is this. So F is equal to 2 into precision into recall by precision plus recall. Okay, now let's keep this and come to this slide to find out how does the value of cutoff, why we are discussing cutoff. Who can tell me? Don't sleep, you are about to get your certificates. We have only 4 more slides, that's it, finishing. So why we are discussing cutoff here? See, how does the value of cutoff affect sensitivity, specificity and accuracy of the model? We are talking about logistic regression. Okay, see that in logistic regression we converted our data to probability, but probability should have threshold, right? Probability can range from 0 to 1. So for a diabetic patient, what is the cutoff? Is 80 and above diabetic or 70 and above diabetic? We need to decide a threshold, right? See that if you plot cutoff and values of sensitivity, accuracy and specificity, the graph will look like this. Also see that the cutoff, when the cutoff of model is increased, its sensitivity decreases. Look at the red line. Okay, and its specificity increases. Why does this happen? See the previous example. We know that diabetes of a patient can range from 0 to 1. I will decide 2 thresholds. One is very small threshold 0.05, one is very high threshold 0.95. Look at what will happen now. Okay, so at the threshold we have drawn a line. All of you can see. Okay, so all the patients who are before the line are considered to be non-diabetic. All the patients who lie after the line are considered to be diabetic. Okay, now with a value of 0.05, cutoff of 0.05, what happens? See that even if a patient has very small chance of being diabetic, that patient is predicted to be diabetic. Why? Because you have put such a small threshold, right? So all the diabetic patients have been correctly identified as diabetic. That is, the sensitivity of the model is pretty high. Model is very sensitive to diabetic patients. Okay, and at the same time a patient is predicted as non-diabetic only if the corresponding probability is very low, even lower than 0.05. It means that the non-diabetic patients have not been identified with the same accuracy. That is, the specificity of the model is not high. Okay, now if I put a very big threshold, very high threshold 0.95, what will happen? Unless a patient has very high chance of having diabetes, the patient is predicted as to be non-diabetic. You can keep eating 10 rasgullas in a day, nothing is going to happen, because the threshold is so high, you will never be caught. You will be always below than that. Okay, so what will happen? All the non-diabetic patients have been correctly identified as non-diabetic. That is, the specificity of the model is pretty high. Specificity of the model is pretty high. Now see that However, a patient is predicted as diabetic only if the corresponding probability is very high, even higher than 0.95. So as a result, diabetic patients have not been identified with the same accuracy. That is the sensitivity of the model is not high. Okay, so did you observe how is the threshold impacting sensitivity and specificity of the model? Putting a low threshold or high threshold directly impacts the usage of your model. If you make your model too sensitive, for example, you open a clinic or a test center and don't properly decide a threshold, and everyone who is coming to your center is getting diabetes, nobody is going to come because you selected a wrong threshold. Everybody is under the scanner. If you select a low threshold, again a problem. Whoever comes to your clinic, they will never come back again to take medicine because all are healthy, right? So threshold has to be selected properly so that you are able to decide whether the patient is diabetic or non-diabetic with respect to this example. Okay, so did you observe how is the cutoff value affecting sensitivity and specificity of the model? Okay, and see that your model is very important because now once your model is ready, you tell me your glucose level, I can tell you you're diabetic or not. But if your model is wrongly calibrated, it can give you some random outputs. Okay, so what we are doing here, what we did here is classify data into diabetic, non-diabetic. So this is your classification task, not prediction task. Prediction we did it in linear regression. Okay, so the entire theory and concept behind linear regression and logistic regression is different because they are designed to serve different purpose. So they cater to different applications. Okay, so time up now. Time for your certificates and high tea. Any doubts? Any doubts?
If you have any doubts, so you can write a mail to sir. Sir will reply and also give some suggestions for finishing your PhD work. So thank you, sir, for entire day for your lecture session. And shortly we will start the valedictory function. So be here only. So your dean already arrived. So we will do it. So.
ವೆರಿ ಗುಡ್ ಈವ್ನಿಂಗ್. ಎಲ್ಲರಿಗೂ ಶುಭ ಸಂಜೆ. ನಾವು ಈ 3 ದಿನದ ಕಾರ್ಯಾಗಾರಗಳ ಅಂತಿಮ ಹಂತಕ್ಕೆ ತಲುಪಿದ್ದೀವಿ. ಐ ವೆಲ್ಕಮ್ ಆಲ್ ದ ಡಿಗ್ನಿಟರೀಸ್ ಆನ್ ದ ಡಯಾಸ್. ಡಾಕ್ಟರ್ ಆನಂದ್ ಸರ್, ಶ್ರೀನಿವಾಸ್ ಜಿ. Now I request our scientific officer Shri V.K. Srinivas to welcome all the dignitaries.
So good evening one and all. So we have completed successfully 3 days workshop in association with your esteemed university. So Director of PG Studies. So sir is here today. Professor H.C. Prakasa sir, Dean PGS US Bangalore. So on behalf of all of you, on my own behalf KST, a warm welcome to you sir for this valedictory function. ಅದು ಬೊಕ್ಕೆ ಕೊಡೋ ಒಂದ. I also welcome our CEO Dr. A.M. Ramesh sir for this valedictory function. Welcome you sir. I welcome today's now resource expert, my dear friend Dr. Uttam sir, for gracing this occasion. Welcome you sir. And I welcome all my colleagues and all of you for this valedictory function. Welcome you all.
Thank you Srinivas ji. I welcome to you all on behalf of all of us. Now I request today's chief guest Dr. H.C. Prakash sir to deliver address this gathering. So voluntarily we request few of you to come here and give your feedback about the training of workshop.
Ladies first. ಯಾರು ಬರಲಿಲ್ಲ ಅಂದ್ರೆ ನಾನೇ ಕರೆದ್ಬಿಡ್ತೀನಿ. ವೇದಿಕೆ ಮೇಲೆ ಆಸೀನರಾಗಿರೋ ಎಲ್ಲ ಗಣ್ಯರೇ ಹಾಗೂ ನನ್ನ ಎಲ್ಲ ಪ್ರೀತಿಯ ಸ್ನೇಹಿತರೆ, ಎಲ್ಲರಿಗೂ ಶುಭ ಸಂಜೆ. ಈ ಸಾಫ್ಟ್ವೇರ್ ಟ್ರೈನಿಂಗ್ ಪ್ರೋಗ್ರಾಮ್ ತುಂಬ ಚೆನ್ನಾಗಿ ಮೂಡಿಬಂತು. ಆ್ಯಕ್ಚುಲಿ ನಾವೆಲ್ಲ ಅಗ್ರಿಕಲ್ಚರಲ್ ಎಕನಾಮಿಕ್ಸ್ ಸ್ಟೂಡೆಂಟ್ಸ್. ನಮ್ಮ ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ನಾವು 8 ಜನ ಅಗ್ರಿಕಲ್ಚರಲ್ ಎಕನಾಮಿಕ್ಸ್ ಸ್ಟೂಡೆಂಟ್ಸ್. ನಮಗೆ MSc ಕೂಡ ಈ ಟ್ರೈನಿಂಗ್ ಪ್ರೋಗ್ರಾಮ್ ಒಂದು ಸಲ ಆಗಿತ್ತು. PhD 2 ಸೆಮಿಸ್ಟ್ರಲ್ಲೂ ಕೂಡ ನಮಗೆ ಪ್ರಾಕ್ಟಿಕಲ್ ಕಾಂಪೋನೆಂಟ್ ಏನಿರುತ್ತೆ ಅದನ್ನು ಸಾಫ್ಟ್ವೇರಲ್ಲಿ ನಮಗೆ ಹೇಳ್ಕೊಡ್ತಾಯಿದ್ರು. ಬಟ್ ನಾವು ತುಂಬ ಡೆಪ್ತ್ ಹೋಗಿ ಬೇಸಿಕ್ಸೇ ಮರ್ತೋಗಿದ್ವಿ ಈ 3rd ಇಯರಲ್ಲಿ. ಆವಾಗ ಅದೇನಂತಂದರೆ ಸರ್, ಇದು ಬಗ್ಗೆ ಇನ್ ಟಚ್ ಇದ್ದರೆ ಮಾತ್ರ ನಾವು ಮಾಡ್ತಾ ಹೋಗ್ಬೋದು. ನಾವಾಗೆಲ್ಲ ತುಂಬ ಚೆನ್ನಾಗಿ ಕಲಿತು ಎಕ್ಸಾಮ್ಸ್ ಎಲ್ಲ ಬರೆದು ಎಲ್ಲ ಮರ್ತೋಗಿದ್ವಿ. ಇದೊಂಥರ ಬ್ರಷ್ ಅಪ್ ಥರ ನಮಗೆ ಫೀಲ್ ಆಯಿತು. ಬಟ್ ತುಂಬ ಚೆನ್ನಾಗಿ ಹೇಳ್ಕೊಟ್ರು ಇಲ್ಲಿ. ಫಸ್ಟ್ ಡೇ ಒಬ್ಬರು ಮಂಜುನಾಥ್ ಸರ್ ಅನ್ನೋರು ಅಗ್ರಿಕಲ್ಚರಲ್ ಎಕನಾಮಿಕ್ಸ್ ಪ್ರೊಫೆಸರ್ ಬಂದಿದ್ದರು. ತುಂಬ ಚೆನ್ನಾಗಿ ಅವರು ಟೀಚ್ ಮಾಡಿದ್ರು. ಸೆಕೆಂಡ್ ಡೇ ನಿನ್ನೆ ಅಂತೂ ತುಂಬ ಪ್ರಾಕ್ಟಿಕಲ್ಲಾಗಿ ಪ್ರತಿಯೊಂದು ಕೋರ್ಸನ್ನು ರನ್ ಮಾಡೋದಕ್ಕೆ ಅವ್ರು ಸೆಂಡ್ ಮಾಡಿ, ಬಟ್ KST ಅವರು ತುಂಬ ಇನಿಷಿಯೇಟ್ ತೊಗೊಂಡು ಪ್ರತಿಯೊಬ್ಬರಿಗೂ ಮೇಲ್ ಮಾಡಿ ನಾವು ಅದನ್ನು ಕೋರ್ಸನ್ನು ಪ್ರತಿಯೊಂದು ರನ್ ಮಾಡ್ತಾ ಹೋದ್ವಿ. ನಮ್ಗೆ ಅರ್ಥ ಆಗ್ತಾ ಹೋಯಿತು ಎಲ್ಲಿ ಸ್ಟ್ರಕ್ ಆಗ್ತಿದ್ವಿ. ಪಕ್ಕದಲ್ಲಿ ಫ್ರೆಂಡ್ಸ್ ಎಲ್ಲ ಹೇಳ್ಕೊಡ್ತಾ ಇದ್ದಾರೆ ಈ ಥರ ಅಂತ ಅಂದ್ಬಿಟ್ಟು. ಆಮೇಲೆ ಎಕನಾಮಿಕ್ಸ್ ಸ್ಟೂಡೆಂಟ್ಸ್ಗೆ ಗೊತ್ತಿರುತ್ತೆ, ರನ್ ಮಾಡ್ತಾ ಹೋಗ್ತಾರೆ. ಬಟ್ ಬೇರೆ ಸ್ಟೂಡೆಂಟ್ಸ್ಗೆ ಇಷ್ಟೊಂದು ಅರಿವಿರಲ್ಲ ಅಂತ ನನಗೆ ಅನಿಸುತ್ತೆ. ಬಟ್ ನೀವೆಲ್ಲ ಹೊಸದಾಗೆ ಕೇಳ್ತಾ ಇದ್ರಿ ಇಲ್ಲಿ ಅಂತ ಅನಿಸುತ್ತೆ. ಈ ಒಂದು ಟೀಚಿಂಗನ್ನು ಸರ್ ಡೀನ್ PGS ಅವರು ಪ್ರತಿ ಡಿಪಾರ್ಟ್ಮೆಂಟಲ್ಲೂ ಒಂದು ಕೋರ್ಸಾಗಿ ಆ್ಯಡ್ ಮಾಡಿಬಿಟ್ರೆ ತುಂಬ ಒಳ್ಳೆಯದಾಗುತ್ತೆ. ಯಾವುದೋ ಈ ಸ್ಟ್ಯಾಟಿಸ್ಟಿಕ್ಸ್, ಆ ಟೈಮ್ ಸೀರೀಸು, ಮಲ್ಟಿವೇರಿಯೇಟ್ ಎಲ್ಲ ಅಡ್ವಾನ್ಸ್ಡ್ ಕೋರ್ಸಸನ್ನು ಆ್ಯಡ್ ಮಾಡೋದಕ್ಕಿಂತ ಅಡ್ವಾನ್ಸ್ಡ್ ಸ್ಟ್ಯಾಟಿಸ್ಟಿಕಲ್ ಪ್ಯಾಕೇಜ್ ಅಂತಾನೋ ಇಲ್ಲ ಬೇರೆ ಏನಾನ ಒಂದು ಕೋರ್ಸ್ ಕರಿಕ್ಯುಲಮಲ್ಲೇ ಹಾಕಿದ್ರೆ ನೀವು ಅದು SPSS ಇತ್ತೋ SAS ಇತ್ತೋ ಇನ್ನೊಂದು ಮತ್ತೊಂದು ಬೇಡ, R ಆಗ್ಬೋದು, ಪೈಥಾನ್ ಆಗ್ಬೋದು, ಅದು ನೆಕ್ಸ್ಟ್ ಯಾವುದಾದ್ರೂ ಬರಲಿ, ನೀವು ಕೋರ್ಸ್ ಕರಿಕ್ಯುಲಮಲ್ಲಿ ಕಡ್ಡಾಯವಾಗಿ ತೊಗೊಳ್ಳೇಬೇಕು ಅನ್ನೋದನ್ನು ನೀವು BOS ಅಲ್ಲಿ ನೀವು ಅಪ್ರೂವಲ್ ತೊಗೊಂಡ್ರೆ ಅದು ಮುಂದೆ ಬರೋ ಎಲ್ಲ ಸ್ಟೂಡೆಂಟ್ಸ್ಗೂ ಹೆಲ್ಪ್ ಆಗುತ್ತೆ. ಈ 3 ದಿನದ ಈ ಕಾರ್ಯಾಗಾರ ತುಂಬ ಅಚ್ಚುಕಟ್ಟಾಗಿ ನಡೆಸ್ಕೊಟ್ಟಿರ್ತಕ್ಕಂತಹ KST ಅವ್ರಿಗೆ ನಮ್ಮ ಎಲ್ಲ ಫ್ರೆಂಡ್ಸ್ನ ಪರವಾಗಿ ಧನ್ಯವಾದಗಳು. ಅದೇ ರೀತಿಯಲ್ಲಿ ಈ ಒಂದು ಕಾರ್ಯಾಗಾರವನ್ನು ಆಯೋಜನೆ ಮಾಡಿದಂತಹ ನಮ್ಮ ಡೀನ್ PGS ರವರಿಗೂ ಕೂಡ ನಮ್ಮೆಲ್ಲರ ಪರವಾಗಿ ಧನ್ಯವಾದಗಳು. ಥ್ಯಾಂಕ್ ಯು ಸೊ ಮಚ್ ಸರ್.
ಲೇಡೀಸ್ ಫಸ್ಟ್ ಅಂತ ಹೇಳಿ ಬನ್ನಿ ಬೇಗ. ನೀವೆಲ್ಲ ಲೆಕ್ಚರರ್ಸ್ ಅಥವಾ ಟೀಚಿಂಗ್ ಫ್ಯಾಕಲ್ಟಿ ಆಗೋರು ಸ್ಟೇಜ್ ಫಿಯರ್ ಇರಬಾರ್ದು, ಬಂದು ಮಾತಾಡ್ತಾ ಇರ್ಬೇಕು. ನಾವೇ ನೆನೆಸಿ ಅಂತ ಹೇಳ್ಬೇಕು. ಇಲ್ಲೇ ಮೈಕ್ ಅಲ್ಲಿಗೆ ಕಳಿಸ್ಬಿಡ್ತೀವಿ, ಅಲ್ಲಿಂದಾನೇ ಮಾತಾಡಿ. ರವಣ ಕೂಡ
ಹಲೋ
ಕೊಡಪ್ಪ ಅಲ್ಲಿ ಫಸ್ಟ್ ಯಾರು ಸಿಗ್ತಾರೆ ಅವ್ರು ಕೊಟ್ಬಿಡ್ಬೇಕು.
Good evening, sir, and all my friends. Already Ramu has added much about the workshop program organized on our software. I would like to add a few points adding upon him, sir. On our whole behalf, we wholeheartedly thank both KSTA and also our Dean PGS for sponsoring this program, because on our own behalf, if we have to pay and attend these kind of programs, definitely we'll put down a step back only. Thanks for giving that support, sir. And this program is like an introduction to statistical software of R. Additionally, if we can extend this program at least to the people who are using R in their methodology aspects, extending this program for another 3 days and providing advanced aspects also, like we people all along with Ramu, I also belong to economics. Certainly in certain using methodological aspect we are stuck in, like we have learned up to here some logistic regression, and sometime in addition to that we have to use some endogenous regression aspect, or additionally we'll be stucking. So providing an additional training to the people at least who are in need, it will help us extra in doing our research. And also we have eminent speakers here that taught us in detail about all the aspects, according to their knowledge it is like teaching ABCD of R to us, but they are very patient and kind enough in explaining all the doubts, and step by step they helped us to run all the codes and all. We once again thank you for that, and thank you for the opportunities.
Good evening, everybody. So for people who are from economics, probably they had an idea as to what our software is, but for us, mostly from food science and nutrition, we had no idea what it was. This is the first time we are getting exposed to this, but that's why the key speakers were actually very patient to start from the very basics and then have enough patience until all of us actually ran the code. It was very helpful, sir. Thank you.
ವೆರಿ ಗುಡ್ ಈವ್ನಿಂಗ್ ಟು ಆಲ್. ಅದೇ ಎಕನಾಮಿಕ್ಸ್ ಅವ್ರು ಹೇಳ್ದಂಗೆ ಅವ್ರಿಗೆ ಮುಂಚೆ ಕೋರ್ಸ್ ಆಗಿತ್ತು, ಅವ್ರಿಗೆ ಅರ್ಥ ಆಯಿತು ಅಂತ ಅಂದರು. ಬಟ್ ನಮಗೆ ಆ್ಯಕ್ಚುಲಿ ಏನು ಬೇಸಿಕ್ಸ್ ಏನೂ ಗೊತ್ತಿರಲಿಲ್ಲ ಆರ್ದು. ಇದೇ ಫಸ್ಟ್ ಟೈಮ್ ಯೂಸ್ ಮಾಡಿದ್ದು ನಾವು. ಪಾರ್ಟ್ಲಿ ಬೇಸಿಕ್ ಒಂದು ಸ್ವಲ್ಪ ಎಕ್ಸ್ಪೋಸ್ ಆಯ್ತು ಅಷ್ಟೇ. ಬಟ್ ನಮ್ಗಿನ್ನೊಂದು ಸ್ವಲ್ಪ ಜಾಸ್ತಿ ದಿವಸ ಟ್ರೈನಿಂಗ್ ಅಟ್ಲೀಸ್ಟ್ ಒಂದು 5-10 ಡೇಸ್ ಇದ್ದರೆ ಜಾಸ್ತಿ ಎಕ್ಸ್ಪ್ಲೋರ್ ಮಾಡ್ಬೋದಿತ್ತು ಆರ್ ಸಾಫ್ಟ್ವೇರಲ್ಲಿ. ಜಸ್ಟ್ ವಿ ಕ್ಯಾನ್ ಯೂಸ್ ಆರ್ ಸಾಫ್ಟ್ವೇರ್ ಅಂತ ಕಾನ್ಫಿಡೆನ್ಸ್ ಬಂತು. ಬಟ್ ಇಂಟು ಡೆಪ್ತ್ ಏನು ಅಷ್ಟು ಗೊತ್ತಾಗಿಲ್ಲ. ಸೊ ಪ್ರಾಬಬ್ಲಿ ಸಮ್ 10 ಡೇಸ್ ಪ್ರೋಗ್ರಾಮ್ ಅನೌನ್ಸ್ ಮಾಡಿದ್ರೆ ಇಟ್ ವುಡ್ ಬಿ ಹೆಲ್ಪ್ಫುಲ್. ಥ್ಯಾಂಕ್ ಯು.
First of all, a very good afternoon to one and all, as a respected Dean PGS and all the dignitaries on and off the dais. I completely agree with the last speakers. I think we were first to be exposed to such a software. In order to use software in our thesis or for our analysis, I think we need still more information, or we need to put our hands. So we need extra another 10 to 15 days of training. So that could be very much helpful for us. And I also request Dean PGS to extend this program if possible in the future, so that at least for our junior batch, that could be helpful for them. So when we go outside to learn such softwares, it's really costly and it is much time consuming, and we cannot make up that time in order to learn. But as Dean PGS has put an effort to bring us here for 3 days and make us learn our software, extremely thank you for your support, sir. And I also thank KSDA for organizing and bringing upon the eminent speakers here. They were very patient, as all of us know, and they were very kind enough to clear our doubts. Thank you.
Your feedback helps us to improve further in future days.
Good evening, everyone. This is Suresh from Department of Entomology. As Ramu said, he represented the economics background students, but I'm being an entomologist and representing non-economic students, and giving some my opinion regarding this training program. Of course, very congratulations to both organizers and Dean PGS, US JKK Bangalore to organize such an wonderful training program for us. This is my second training program on our software. Before that, I have attended around 10 days training program, which is being organized in our US JKK itself. That time I requested our Honorable Dean PGS sir to extend this 10 days to 15 days. I think sir remembered that, but unfortunately 10 days has been reduced here to 3 days. Still, we have learnt a lot of things, but what I felt is, instead of I feeling it as an R software, most of the time I felt it as an statistic training course. So, which is, of course, without statistics, we can't go for the analysis by using the tools. But one thing I can request the organizers that before conducting such a great events, it is better to get the audience, or you can say the trainees which we are going to select, the opinion of those students, that what are the things you are expecting from that particular training program. So for example, the few people are working on the some aspects which are really they want to work with the R softwares. So and few people want the particular things from the R software. So like that, if you give any option for the students to give their feedback before starting this one. So what are the things you are expecting this particular training program? So that based on that, if you build up the course content, that will be more helpful than conducting directly. So one thing that I expected from this training program. Besides this, everything went very nice, and in the discussion also, all the resource persons has given a lot of information for us. Either it may be statistical or with respect to the R software. So once again, I thank Dean PGS sir and this KSTA for giving us such a wonderful opportunity for me to be part and parcel of this particular program. Thank you one and all.
Thank you very much for the volunteered and non-volunteered. I mean, most of the feedbacks were first one, but your inputs will be taken care in future programs. Now I request Chief Guest Dr. H.C. Prakash sir to deliver the address.
on the dais, Ramesh sir, Srinivas sir, and the Uttam Kumar sir, and all my dear PG students. Of course, feedback is very good. Only 3-4 people are given out of 63, 65 students. Of course, for economic students, it's only a basic. I think it is a we have. I think it's like it has been given like a reorientation, so that I think you understand 100%, right? For the economic student, for rest of the other students, of course, software is this software is very new. Giving this software for 3 days or even 7 days, it's not sufficient. Of course, in the beginning, we tried an attempt give the software this one, but during that time, some administration problem was there. That's why it was not possible. Of course, KSTA, they came forward to offer this course. Of course, whatever the best they have given, it has been given here, I hope, because seeing your faces, I can tell something good you have imbibed from this program. Of course, this program is only a continuity program. If at all, if you want to learn something here from here, they have given the basics. From basics, you can join some other course in the wherever the programs are running in the city or any other training centers. There you can learn it, and if need for your employer, we can equip with this tool. So that is most important. Only thing is, we are just introducing. These are the softwares where you can very useful for your research work and also for your employment. With that context, so that therefore the ICR and other things, they are encouraging these type of training program for all the students. In that context, in that amount, basically we are giving our software Python programs. Previously we have given Python program also, some basics like that. So whatever the things are there, we are selecting the best people. Of course, whatever the things are there, they have given the best people. They have given a very good training program on this. I think some basics should be there. Something is there in your mind. Henceforth, as I told earlier, depends on the need or requirement of the employer, or if it is required for your research. If you go outside USA and European countries, these type of courses are very costly. You may not afford for your research work. Under such conditions, this will become a basics, so that you can enhance your knowledge by data collections, reading, studying the things, and by the help of your teachers here. With that context, we have made this attempt. Of course, this program has become very well. Congratulations all the students having patiently involved here. Of course, it's a new atmosphere. Always staying in the GKVK, it's simply boring, you know. Coming here elsewhere and learning and listening to some other new teachers than the regular teachers. It's always very good, especially for the students. So I think we have enjoyed very well. Of course, this center, of course, very prestigious, the institute, because this is established by U.R. Rao, the former chairman ISRO, now presently the S. Ayyappan, our DG ICR. This only the aim is to give the foster the or improve the technology and popularize the technology, science and technology among the public. Accordingly, they have delivered this software, that is our software introduction to statistical data analysis using our software for 3 days program. It has come up very well. On this occasion, congratulations once again having successfully completed this program. If anything is there, we'll think in future, next year. If funds are available there itself, whatever things are, we take according to your feedback. Or even if you come forward and ask, sir, this is the thing we want, accordingly we will plan and give and ask the such of those teachers, and will make these things to complete, so that you will become full knowledge on these type of programs. So on this occasion, sir, we extend very thankful to the institute, especially Anand sir, because he has taken so much of interest in this training program, and also Srinivas sir, he has come to our directorate and visited us and appraised the things. On this occasion, on behalf of University of Agriculture Sciences, Bengaluru, and Directorate of PG Studies, Postgraduate Studies, we profusely thank this institute, Karnataka State Science and Technology Academy, and the CEO, the Anand sir, and the Ramesh sir and the Srinivas sir and all the staffs here who have coordinated very well, made this function very successful. So thank you so much. Thank you one and all.
Thank you very much, sir, wholeheartedly from KST and all of us here. Now, certificate distribution. Yes. Now I request our CEO, Dr. M. Ramesh sir, to address presidential address. Yes, sir. Yes.
ಇದು ಫಸ್ಟ್ ಕ್ವಿಜ್ ಕೊಡೋ
I request our colleague Shantaraju to announce the winners and give the certificates. Sir, score graph. Score graph. Score graph you can see like this. ಇಲ್ಲ ಹೇಳಿ ಎಲ್ಲ ನಾನು ಬರ್ತೀನಿ ಇದೇನು 12 ಬಂದಿದೆಯಲ್ಲ ಫುಲ್ ಟೈಪ್ ಇದ್ರೆ ಹೇಳ್ಬಿಡಿ First we will announce third prize. 3 people have
ಮಾರ್ಕ್ಸ್ ಎಲ್ಲಿಂದ ಎಲ್ಲಿವರೆಗೆ ಮ್ಯಾಕ್ಸಿಮಮ್ ಎಷ್ಟು ಲೋಯೆಸ್ಟ್
low.
ಇದೆಲ್ಲಿ ಬರ್ಕೊಂಡಿರ್ತಾರೆ
ಊಟದ ಸಮಯದ ಮೊದಲೇ ನಡೆದಂತಹ ಕ್ವಿಜ್ ಕಾಂಪಿಟೇಷನ್ ಸ್ಪರ್ಧೆಯಲ್ಲಿ ಒಟ್ಟು 58 ವಿದ್ಯಾರ್ಥಿಗಳು ಭಾಗವಹಿಸಿದ್ದು, ಅದರಲ್ಲಿ 7 ಜನ ಪ್ರಥಮ ಮತ್ತು ದ್ವಿತೀಯ ತೃತೀಯ ಬಹುಮಾನಕ್ಕೆ ಆಯ್ಕೆಯಾಗಿದ್ದು, ಉಳಿದ 50 ವಿದ್ಯಾರ್ಥಿಗಳಲ್ಲಿ ಗ್ರಾಫ್ ವೈಸ್ ಅವ್ರ ಡೀಟೇಲ್ಸ್ ನೀಡಲಾಗಿದೆ. ಇದರ ಅರ್ಥ
blue represents students, red orange represents your score.
ಫಸ್ಟ್ ಒನ್ನು ಒಟ್ಟು 17 ಅಂಕದಲ್ಲಿ 13 ಅಂಕವನ್ನು ಪಡೆದಿರೋ ಫಸ್ಟ್ ಲಿಸ್ಟ್ ಇದೆ ನೋಡಿ, ಅವರಿಬ್ಬರು ಮಾತ್ರ. ಸೆಕೆಂಡ್ ಒನ್ನು 14, ಸೆಕೆಂಡ್ ಒನ್ನು 17ಕ್ಕೆ 13 ಇಬ್ಬರು, ಮತ್ತು ಥರ್ಡ್ ಒನ್ನು 17ಕ್ಕೆ 12 3 ಜನ. ಉಳಿದ 50 ವಿದ್ಯಾರ್ಥಿಗಳಲ್ಲಿ ಈ ರೀತಿ ಪ್ಯಾರಾಗ್ರಾಫ್ ಸ್ಕೋರನ್ನು ನೀಡಲಾಗಿದೆ.
ಈಗ ಥರ್ಡ್ ಹೇಳಿ.
ಥರ್ಡ್ ಪ್ರೈಸ್ ಸುಪ್ರಿಯಾ ML. ಪ್ಲಾಂಟ್ ಪ್ಯಾಥಾಲಜಿ. ಫಾರೂಕ್ ಖಾನ್, ಇವರು ಡಿಪಾರ್ಟ್ಮೆಂಟ್ ಆಫ್ ಪ್ಲಾಂಟ್ ಪ್ಯಾಥಾಲಜಿ. ಮುತ್ತುಗೌಡ
ಯಾವ ಡಿಪಾರ್ಟ್ಮೆಂಟ್?
ಬಯೋಟೆಕ್ನಾಲಜಿ.
ಪ್ಲಾಂಟ್ ಬಯೋಟೆಕ್ನಾಲಜಿ. He scored well.
Each 3 members. ಸೆಕೆಂಡ್ ಪ್ರೈಸು ಕೆಂಪರಾಜು M.
Genetics and plant breeding.
ಪರಮೇಶ್ ನಾಯಕ್.
Parmesh Naik agronomy. Second prize. They scored 13 out of 17. ಇಬ್ರು ಪಕ್ಕ ಪಕ್ಕ ಕೂತಿದ್ರಂತ.
ಇನ್ನೊಬ್ರು
ನೆಕ್ಸ್ಟ್ ಫಸ್ಟ್ ಪ್ರೈಸ್.
ಫಸ್ಟ್ ಪ್ರೈಸ್ ಬಾಲಾಜಿ. ಸುರೇಶ್ R. ಇವರು ಸರ್ ಬಾಲಾಜಿ, ಸುರೇಶ್.
ಸುರೇಶ್ ಯಾವ ಡಿಪಾರ್ಟ್ಮೆಂಟ್? ಎಂಟಮಾಲಜಿ ದೇ ಸ್ಕೋರ್ 14. ಓ ಏನ್ರಿ ಇಬ್ರು ಪಕ್ಕ
ಅಷ್ಟೇ ಸರ್.
ಹೌದು ಸರ್, ಸಮಥಿಂಗ್ ವೆಂಟ್ ರಾಂಗ್.
ವೆರಿ ಗುಡ್.
So, thank you. And no, many of them scored less than 10. They have scored around 17 students, and 10 scored around 19 students. So 11 scored around 13 students. So this is the graph. 7 students are more attentive, and 19 students are attentive, and 26 are less attentive, and not attentive 6 people. So this is the graph. So yes, our CEO sir first day told we have inserted the sensor. So that graph we took it and we plotted. So this is the thing, we got it. Yeah.
Now we call upon the names of students to receive the certificates. Apsara TN. Apsara TN. Arvinda BJ, Research Scholars. Gagan B Shetty. Hanumanta D Lamani. Gagan ಇಲ್ಲ. ಹನುಮಂತ್ ಡಿ ಲಮಾನಿ. ರೋಹಿತಾ ಡಿ ಎಸ್. ಶಾಫ್ನಾಸ್ ಐ. ಶಾಫ್ನಾಸ್. ಶಾಜಿಯಾ. ಶಾಜಿಯಾ KL. ವಿಮಲಶ್ರೀ H. ಕೆಂಪರಾಜು M. ಕೆಂಪರಾಜು M. ಸುಪ್ರಿಯಾ ML. ಕೆಂಪರಾಜು. ಮಲ್ಲಿಕಾರ್ಜುನ್ ಶೇರ್ಖಾನೆ.
ಸುಪ್ರಿಯಾ.
ಪಲ್ಲವಿ CR. ಅರುಣ್ ಕುಮಾರ್ M.
ಪಲ್ಲವಿ.
ಜಯಶ್ರೀ. ಅರುಣ್ ಕುಮಾರ್. ಜಯಶ್ರೀ. ಪೋತಾಲ ಹರ್ಷಿತಮಾಲ. ಸುಷ್ಮಿತಾ C. ಅಶೋಕ್ ಪ್ರಿಯದರ್ಶನ್ AM. ಮುತ್ತುಗೌಡ. ಭರತ್ M.
ಅಶೋಕ್ ಪ್ರಿಯದರ್ಶನ್. ಮುತ್ತುಗೌಡ್.
ಫಾರೂಕ್ ಖಾನ್. ಮೊಹಮ್ಮದ್ ಸುಹೇಬ್ ಇಸ್ಮಾಯಿಲ್. ಪೂಜಾ PS. ಶದಬ್. ಶಿಲ್ಪಾ N.
ನೆಕ್ಸ್ಟ್ ಹೇಳ್ತಾರೆ ಬನ್ನಿ.
ಸಿದ್ದು ಬಸವರಾಜ್ ಚಿಂದಿ.
ಶಿಲ್ಪಾ.
ಬರ್ಬಾರ್ದಾಗಿತ್ತು. ಸೌಮ್ಯ MS. ಸುಮಾ K. ಚಂದನ್ ಮಂಜುನಾಥ್ ಗುನಗ. ನವ್ಯ VG. ಪೂಜಾ ರಾಜೇಂದ್ರ ದಾಂಗೆ. ಶ್ರುತಿ ಕೋಲೂರ್.
ನವ್ಯ.
ಇದೊಂದ್ಸಾರಿ ಕನ್ಫರ್ಮ್ ಮಾಡಿ.
ಪೂಜಾ ರಾಜೇಂದ್ರ ದಾಂಗೆ.
ಶ್ರುತಿ ಕೋಲೂರ್. ಶ್ವೇತಾ VR. ಅಂಬಿಕಾ. ಅಂಬಿಕಾ, ಕಲ್ಪನಾ ಮುಗುಳಿ, ಕಾವ್ಯ ಎಮ್ಮಿ, ಮೀನಾಕ್ಷಿ ಜೆ, ನವೀನ್ ಕುಮಾರ್, ಸಂಕೇತ್ ಅಶೋಕ್, ಸಂಕೇತ್ ಅಶೋಕ್ ಯು, ಸತೀಶ್ ಕುಮಾರ್ ಆರ್, ರಮೇಶ್ ಶ್ರೀ ಎಸ್ ಆರ್, ಸಹನಾ ಎಚ್ ಎಸ್, ನಿಸರ್ಗ ಬಿ ಎಸ್, ಮೊಹಮ್ಮದ್ ಐಶ್ವರ್ಯ ಅನಿಲ್ ರಾವ್, ಪರಮೇಶ್ ನಾಯ್ಕ್, ಸೌಮ್ಯ ಕೆ, ಸ್ವಾತಿ ದಾಸ್, ವಿಘ್ನೇಶ್, ಅಕ್ಷತಾ, ಆರ್ಯ ಸುನಿಲ್, ಧೋನಿಯಾ, रचना के पवार, पी निहारिका, मनोहर के एन, अभिनंदन के आर, अभिनंदन अभिनंदना सॉरी, अमीर पाशा, प्रियदर्शिनी एस, यशस्विनी एम एस, ज्योति जड़ी पूजारी, महांतेश, नागनगौडर, धर्मराज बी एम, गुंतु कोगुला पट्टाभी संदीप, लक्ष्मी मुरली कृष्ण, सुरेश रामकृष्ण जंबगी, विनोदा, विनोदा, चैत्रा एन्नार, देंचवा खार, सुमन के एम,
दैनिचवा,
कविता एचन, नलिनी श्री आर एन,
कविता,
नंदिनी एच एम, रामू एम एस, सीमा कौसर, वैष्णवी, एना जोस, बालाजी बी एन, भार्गवा सी एन, कोप्पर्ती अमृतावल्ली, रेणुका हिरेमठ, Congratulations to all and thank you. Now I request our CEO Dr. A.M. Ramesh sir to deliver presidential address.
Good evening. ನಮ್ಮ ಡೀನ್ ಪಿ ಜಿ ಎಸ್ ಪ್ರಕಾಶ್ ಸರ್ ಹೇಳ್ದಂಗೆ ಯು ಆರ್ ಆಲ್ ವೆರಿ ಎಂಥೂಸಿಯಾಸ್ಟಿಕ್. ಇನ್ಫ್ಯಾಕ್ಟ್ ಸರ್ ಹತ್ರ ಮಾತಾಡಿ ಇನ್ನೆರಡು ದಿವಸ ಎಕ್ಸ್ಟೆಂಡ್ ಮಾಡೋಣ ಅಂತ ಇದ್ದೀನಿ ಟ್ರೈನಿಂಗ್ ಪ್ರೋಗ್ರಾಮ್. ಆರ್ ಯು ಓಕೆ ವಿತ್ ಇಟ್? ನೋಡಿ ಸರ್. ಓಕೆ ಓಕೆ, ನೆಕ್ಸ್ಟ್ ಟೈಮ್. Hearty congratulations to all of you. All of you were attentive. Of course, that graph was not correct. Most of you were attentive. Only one or two were not attentive. I got the information on my computer that all of you were attentive. One or two were dozing off. That's why it gave a wrong signal that 7 were not attentive. Very good. Keep it up. Thank you very much for your patience, perseverance, and being with us for the last 3 days and learning a lot of statistics. In fact, this is just a basics. You have to build up on the basics. We can't teach everything. We will give only modules, basics. Based on that, you have to build up. In future, maybe we'll organize an advanced statistical and R software program. Probably by that time, many of you would have joined some institutes or as a teaching faculty or a scientist. But for next future PhDs, we'll be organizing both basics and advanced trainings. You'll be enthused to organize such programs when attendance is more. For the last 3 days, I have observed and took feedback from my colleagues that most of you are present. Even after lunch, you are alert and active. That's really great. Keep it up. I'm sure all of you will succeed in your life. I wish you a great future. Thank you very much for being with us. Thank you.
Now I request, thank you very much sir. Now I request Vikesh Srinivasu to deliver a vote of thanks.
So good evening Unadal, respected dignitaries on the dais and my dear friends. So we have completed 3 days introduction to statistical data analysis using our software. So it's a hands-on training workshop. So first of all, I heartfelt thanks to Dean PGS sir, Dr. Prakash sir, for his kind support and encouragement to organize this workshop for you people to motivate you to learn these kind of basics and publish your research articles in a very good journals. That is their motto, and also finish your thesis within a good data graphs and other things for your results. So with this I must thank on behalf of KSTM, my own behalf, heartfelt thanks to Prakash sir and also Banu Prakash sir from the Director of PG Studies. Thank you very much sir. Please accept our small gift as token of respect. And also I must thank our chairman of KST, Professor Ayappan sir, and also our CEO Dr. A.M. Ramesh sir for always supporting and encouraging us to organize these kind of programs. Thank you both of them for their wonderful support. Thank you very much sir. I must thank Triple ITB Professor Uttam sir and team. Whenever I call, they always agree for whatever. If they have a busy schedule, also they will agree for KSTA talk. That is really, I don't know what relationship we have. So really, he is very humble to come here and give the talk. And even though he is a lot of busy schedule, lot of projects, he is guiding many PhD students. He is going abroad, and also ISRO people are inviting him for the meetings. Even though he is agreed for KSTA, today he had a class, but he actually skipped that class and he came for KSTA, the KSTA call. I must thank his Uttam sir and his team for coming here and giving their lectures. And thank you very much sir for your always humble nature and kind acceptance of our invitation. Thank you, sir. Please accept. I must thank all my colleagues. So we are like, teamwork. So no, I don't want to tell all the names, but the first day I told, but all my colleagues really they did supported me to organize this kind of workshop. Even from day one, before that also for preparing. So bringing all these mementos and other things, notebook and also folders and pen and everything, even for food arrangements, everything. They have supported, even making the certificates, printing, and all those things. I mean, taking attendance and everything. So all my staff, it is like a teamwork. We did it. So I must thank heartfeltly to all my colleagues of KSTA, and also all of you gathered here. And I thank you very much so for your nice presence here for all the 3 days and patience hearing of this 3 days workshop. I must thank you, and also I say gratitude to your Dean PGS and Director of PG Studies. Thank you very much, sir. Thanks. And once again, sir, I told sir already. First, I told Ramesh sir and also Ayappan sir for their support. Thanks. Thanks you one and all, and I wish you all a bright future in your future endeavor. Thank you one and all. Thank you, sir.
On behalf of all of you, I thank my colleague Mr. Srinivas, who has been with you for the last 3 days. In fact, he doesn't stay in Bangalore. He doesn't stay in Bangalore. Every day he travels to Tumkur. He left Tumkur for 3 days for this program. On behalf of KSTA and all of you, thank you very much.
Thank you, sir. So one group photo.
Request all of you to follow our website, subscribe to our website for future programs and activities. You can follow us in all the social media accounts, and you can, those who have not given your feedback, you can write to us through email, or you can mention it in the Google website. Thank you.